Good morning, Peter.
Good morning. My coffee is, I just hear the water is finished boiling.
Nice. You managed to time shift pretty successfully.
Don't tell me. No, it's not as successful as it looks. Don't worry.
I see. Hello, Ana Carla.
Coffee.
Yes.
Hi. Hi, Peter. I'm Anna. I'm your backup manager today. So
Yeah.
I'm going to be here if you need something.
Good. I was worried because I did sleep 2 hours, then I woke up.
Oof.
Was awake for 2 or 3 hours. I watched this movie called about that American spy guy that Ed Snowden. There's a movie about him. Watch that instead.
And then go back to sleep?
I slept for an hour and a half again. But room manager is my favorite job.
Yeah, you get to do stuff and time passes fast. So the chair today should be Christophe.
And the backup chair?
Me. Let's see. So we got some people joining. We have also one speaker for today, Fenya. And
good morning. Can you hear me?
Yep.
Oh, wonderful.
So Fenya, are you using the same setup as Kai?
Yes, I'm doing. This is why I really need to stress out that I'm not going to share my screen.
Okay.
Well, I will do this as a backup solution if everything is collapsing, but let's hope this is not happening. So I'm streaming a video where you see my face sometimes, my slides sometimes, depending on what I'm telling by now. So you can rely on when you see my face, it's not necessary to see the slides.
Okay, cool, excellent. So let's give it a try. It's a fancy setup that you have, folks, over there, right? At HITS.
It is, yeah. I'm pretty excited, actually.
So HITS is in Heidelberg, is that right?
Yeah, that's correct.
Ah, that's nice. That's nice. Heidelberg is a nice city.
Yeah.
It's very nice.
For 2 years now, it's pretty nice.
Is my microphone on? Yes. I hear rumors that ADASS might be there in a few years.
Oh yeah, I had that rumor too. So looking forward.
You are on the list. Yes. I think there's competition, mind you. I think there is 2 other sites that are sort of penciled in.
Yeah. So
I don't think we ever actually have a competition. People sort of automatically go, okay, you go first. And
it's like the after you problem, as a computer scientist would say.
So, Francesco, were you successful in auto-assigning people, the speakers, to the forum, or do we indeed pick them up?
It's a mixed bag. You can see that Fenya, for instance, joined directly as a panelist, and also Giuseppe, who's also one of our speakers today, joined directly as a panelist. But Zoom doesn't seem to be as smart as we would like it to be. And sometimes people click on the link and they become panelists, sometimes they don't. So for instance, Christophe, who will be the chair, is there as an attendee. So I moved him already because I also have to give him co-host status.
Yeah, so I got the email and I linked through that panel, but I don't know if you already pre-assigned me or if that's a different link from the other people.
In theory, Zoom should be smart enough, right? So Zoom should recognize you by your email address and should just do the right thing, but it doesn't all the time. It does most of the time. Sometimes it does bizarre stuff, but most of the time it works, I would say. Most of the times.
6 o'clock. Okay, I'll be right back. I'm going to, so my backup can pay attention. If
Yeah,
Matthew
sure.
is
No,
showing, if
no
Matthew
worry.
is showing up.
Okay.
I'll be right back.
And I'll put the slide, the starting soon slide, so that people don't get too confused. Good morning, Christoph.
Good morning, Francesco.
I will mute my microphone and get out of your way.
Okay, no problem. So, but Francesco, so just for me to remember, how do I give the floor to the speaker?
You just ask them to unmute, turn the video on if they want to, and share the screen if they want to. You know, for instance, Fenia, who's going to be using the same setup as Kai. By the way, she will not be sharing her desktop. She will be doing the video only, because they have this setup where you can see the slides and stuff like that.
Which person, which speaker did you say? Fenia.
Fenia, that will be the first oral contribution after the break.
Okay. Yeah. Okay.
I think we can even test this if we switch from the camera to the slides, just that you have an idea how this could look like.
Yeah. Okay.
Geht das gerade? Alles klar. So I'm starting my camera now, and now you should see the slides. Is this correctly?
We see the slide in your camera.
Yes,
yes,
that's correct. You see it in my camera, so you have to scale the camera a little bit up, because this is the only thing you will see, only my camera. And if we switch now to myself, you can see me. Hi.
Hi.
Yeah. No, from another angle.
Yeah.
All right, and now the slides again.
Okay.
So yeah, that's it.
Okay, good. Good morning, Matthew. I think you need to unmute yourself, Matthew.
Ah, yes. Good morning. How are you?
Good morning. Fine. And you?
Yeah. Well, it's evening here, so.
Yes, it's early morning here.
Yeah. It's been a long day.
So you're the first one, huh? So maybe we can
Yes.
try the test. So
Let me try sharing my screen. Is that working?
yes, perfect. Yeah.
Okay.
So you have 25 minutes plus. Then I'll give you the. I mean, will you have a timer next to you, or do you want me to make you a sign, or tell you 5?
Let me get a timer.
In the meantime, can you still hear me?
Yes.
Wonderful, because I switched my microphone just to make it sure. Thank you.
Okay, you're welcome. So people are starting to come in.
It's early for you.
Yes, it's going to be even worse next week at the IVOA because it's going to be even one hour earlier start. But probably better for you.
Yeah, I'll have to see. There are too many things going on at the moment. There are sort of 2 or 3 separate meetings all happening at the same time this week and next week. So I have to see how much of the IVOA I can actually go to.
It's always that's one of the downsides also of this virtual meeting is that the normal meetings are continuing.
Well, no, that's it. So you can actually do more because you're all in the same location. You don't have to travel or anything, but it also means that you get double booked more quickly is what I'm finding.
Exactly, that's what I meant. Yes.
Yeah. I mean, in normal times, I would be in Granada now, and I wouldn't be doing some of the stuff I was doing earlier today or last night. So,
Yes. Slowly increasing. The number of participants is slowly increasing.
well, it's late or early, depending on where you are. So,
Yeah.
I guess this is sort of the ideal time slot for Moscow.
Yes. Yeah. Or for Asia in general, probably.
Yeah.
Also, Noria is saying that it's a good time.
Yeah.
Okay.
Shall I start sharing my screen?
Yes, maybe we can do that, yes. So, hello, everybody. Good morning, good evening, good afternoon, wherever. So, welcome to this, this session at ADASS. So, the first invited speaker is Matthew Graham, well known to this community. Matthew is a professor of astronomy at Caltech and also the project scientist of the CET transient facility, and he's going to speak about the lessons learned from their first 300 million alerts. So, Matthew, the floor is yours.
Thank you, Christoph. Thank you very much for the organizers for inviting me. I would hopefully have been in Granada today, but obviously I'm not. In spite of my background, I'm actually still in Pasadena. So I want to take you back about 12 years to ADASS 18 in Quebec, about this time of year, where I gave an invited talk, the last invited talk I've given at an ADASS, on what astronomy in 2020 would look like. And there were a number of predictions I made in that particular talk, and you can go and look at your ADASS proceedings from then. Back in 2008, we said that LSST would be operational in 2014, so we would now be in year 6 of LSST. LSST would require one of the top 1,000 computers in the world. SKA would have been coming online this year, and it would have required the top computer in the world. And I predicted that we would wake up every morning, and instead of astronomy picture of the day, we would be looking at the universe today, which would be a morning digest summarizing changes in the position, the flux, the spectra, etc., of billions of objects that we were monitoring in multi-wavelengths across from the local solar system out to the most distant galaxies. And so you'd get a daily summary or a morning summary of the things that had changed in the universe while you'd been asleep, and so you could figure out what was interesting. We were expecting that we would be dealing with petascale or maybe even exascale alert streams, and that we would require web scale computing resources just to process this torrent of data. We had these notions that, however, that disparate set of events could be linked together in some way with archival or supplementary data in a machine comprehensible way, that we would have representations that both the human could read and the machine could process. And we thought that the way forward was with linked data, with RDFA, with the semantic web. We also thought that actually much of the data mining and analysis with these large alert streams would be performed by intelligent agent avatars that would be existing out there in the cyberspace somewhere, and that we would not be doing a lot of the processing ourselves. We would be just looking at the results and making the policy decisions or figuring out what was interesting. We noted that there would be a problem of merged clouds, hypervisors, the buzzword of 2008. We were concerned that these cloud environments, the different cloud environments, how would I integrate across all of those providers who are making this sort of web scale processing available? We identified that to handle this, we would have to be doing declarative parallelized programming in a language called Curry. I think that has completely died the death. I haven't heard of Curry since. I mentioned in my talk 12 years ago. We also predicted that the bulk of astronomical data would no longer be in relational database systems, but in NoSQL or key values pairs or something like that. And I ended my talk and the subsequent publication by saying that I would be prepared to come back in 12 or 13 years' time and give Astronomy 2020 reflections on where I went wrong. Well, here I am now. And so this talk is actually sort of building on where we were there with that mindset, and where we are with the state of the art. We don't have LSST yet. We don't have SKA yet. What we do have in 2020 is ZTF, the Sticky Transient Facility, for which I am the project scientist. And let me give you a very quick overview for those who are unfamiliar with this. This is a survey that's been running for 3 years, and we've just had our renewal of a further 3 years, we used the 48-inch Schmidt telescope at Palomar Observatory, which is the telescope that was used back in the 50s for the original POS survey on photographic plates, but we've replaced the photographic plates with a large CCD detector, 16 CCDs, 47 square degree field of view. With a 30-second exposure, we can survey about 4,000 square degrees an hour. As I said, we're nominally 6 years. We've just finished our first 3 years. We're moving now to, because the way that the project is funded, we spend half of our time on public surveys, which is now a 2-night cadence of the northern sky visible from Palomar Observatory and GNR. And then 30% goes towards the ZTF partnership and 20% is for Caltech programs. The partnership and Caltech also have an I-band filter that they can use. I say nominal exposure time is about 30 seconds. That gets you to a 20.5 depth. We have about 2 arc-second image quality. And whole northern sky from deck of -30 above. We send out real-time alert streams, which is one of the big things that ZTF has done for the community in preparation for LSST. We send out several 100,000 alerts per night of things that have changed in the thousands of square degrees that we survey every night. VO event, which was the old IVOA alert format, was not sufficient for the data that we wanted to pack into an alert structure. And so whereas Catalina Sky Survey that I've previously worked on sent out a small number of VO events a night, for the industrial scale alert stream that we wanted going forward with ZTF, we came up with an Avro-based packet. So Avro is an industry standard for messaging. And most importantly, it can contain binary structures. And the binary structures that we wanted to put into the alert packet was the thumbnails showing the new image, the reference image, or the template in LSST parlance, and the subtraction between the two, which shows you what the transient is. We have unique spatially matched alert names, which have these sort of 7-character alphabetic strings. We also include a 30-day rolling window light curve history. So there's a 30-day photometric history of that particular transient from ZTF data. We include then a whole load of other metadata in our alert packets. The alert packets are typically about 80 kilobytes in size, 85 kilobytes in size. Some of those additional data is the real bogus score. So we have certain machine learning classifiers which run over our data and give you information: distance to the nearest pan-star sources, distance to the nearest solar system object, some degree of alert history, that sort of thing. So that's the alert packet. That's the infrastructure we've built up, which is sort of similar to some of the stuff we thought about back in 2008, I guess. We've fostered an alert brokering ecosystem, trying to get the community ready for LSST and other projects. So we've encouraged those who want to be LSST brokers to sign MOUs with ZTF, and so that they can get the infrastructure in place for filtering, get community users in, start making their own discoveries. There's the Alerce broker in Chile, Lasser at Royal Observatory Edinburgh, Fink in France, Antares from Noir Lab here in the US. LCO has a simpler one, and one of our newest ones is the multi-messenger astrophysics initiative that's being led from NCSA. They're all serving these to some degree of the community, providing slightly different flavors of filtering, slightly different flavors of classification, and getting ready very much for LSST. So this is a good thing that ZTF has provided, and one of the things that's a very good success, we think, for our survey. So ZTF-1 officially ended on September 30th this year. It ran for 929 nights. Data was taken on 734 nights. A total of 480,000 exposures overall. 22 million square degrees of sky was surveyed. That's equivalent to what LSST will do in its 10 years. As I say, we've got a larger field of view. So in terms of just 2D sky coverage, we've now surveyed the same amount of sky that LSST would do in its 10-year run. Out of that, we've produced 300 million alerts. About 100 million of those come from the public data stream. More come from the private data streams because we have higher cadence observations. About 6.5 million of those associated with known solar system objects. We've done 3 data releases to date. The next one's coming in December. That's 5.6 billion sources with light curves in GRI. We ourselves, the project, have produced over 90 publications, and there are lots of publications now coming as the community catches up and starts trawling through our data archives, through the alert archives, as well as the real-time stuff. In terms of the science that we've generated, 5,000 supernovae, I think at least half of the supernovae detected now are and reported to TNS are coming from ZTF. Tidal disruption events, changing look quasars, neutrinos from tidal disruption events associated with our detections, ultra compact double degenerate binaries in the galactic plane that will act as LISA sources, asteroids, comets, asteroids within the orbit of the Earth, asteroids within the orbit of Venus, but no Planet 9. Lots of LIGO follow-up, but no neutron star, or black hole, neutron star EM counterparts, but possibly a black hole counterpart. So as you would expect for any modern sky survey, generating lots of science, LSST will do even more, etc., etc. Some of the problems we face is it turns out that we've probably been the most complex time domain survey ever scheduled, not because it's not just a case of us doing that nightly or bi-nightly, tri-nightly scanning of the galactic plane and the northern sky. Because of the way that we are this 40%, 20% funding and broken up, each of those has their own separate servers that they want to put in, and trying to put those all together has been a real challenge. And Eric Bellum at the University of Washington has developed a scheduler that's been very effective on this. Almost 90 survey configurations, filter exchanges, target of opportunity events, all that sort of thing, a real success. But one of the things that you might not have thought of for just a simple sky survey. We're not actually a simple sky survey. We're quite a complicated sky survey in those sort of things. So going back to those original ideas we had in 2008, how do those factor, or how do those join up with some of the things we're seeing? So this whole idea of, the fire hose is the thing to be worried about, the data volumes, etc., is it's completely not true. We have the technology. ZTF is a 10% LSST according to a number of metrics, including data volume, data processing. We can easily scale up by a factor of 10 to get there with what we have in terms of infrastructure, in terms of computing. So we have the technology to handle the volume and such. So that's definitely not an issue. And we're very clear on that, I think, now. One of the things that we've noticed, however, is that even within the ZTF partnership, there is an effort to reinvent the wheel many times. Individuals, groups attempting to solve the same problem. I think we see that as well in the brokering communities. We have 15 to 20 brokers vying to be LSST brokers. They're all facing the same sort of problems, and a lot of them are working within their defined funding communities, which is to be expected. But it means that with finite resources, trying to tackle the same problem, we're maybe falling short of areas where we should be addressing things. And I think that's certainly one of the things that we've seen from ZTF, as I say, both within our own project and also in the broader community of people who are trying to use ZTF alerts and that sort of thing. So that's one of the things that we really should work as a community to get around. There's this whole idea of, as I said, back in 2008, we thought we'd all have intelligent agent systems working on this. So we'd have machine learning plus the right sort of training data sets, and then humans in the loop to do the labeling, but we could take those out. The problem is we haven't taken the humans in the loop out yet. And that introduces latency, inefficiency, and non-repeatability into a lot of the things that we want to have, where we want the machine learning actually to be doing a lot. We still have people who are doing daily scanning of alert streams when we should believe the rule sets or the AI systems that we've trained to be able to identify the things that are in string and just leave those to put that in. So we don't have enough confidence yet in our machine learning to move fully into the AI in the loop. And you would have thought that we would have been there. I think, in 2008, we would have thought that in 12 years' time, we would have a much stronger reliance on machine learning and AI, particularly with the rise of deep learning in the last 5 years, than is necessarily the case in what we're seeing now. We're finding also that the history is important, that in the alert streams itself, that alert structure, you don't just want to know what has changed, but you want to know what is the history over the last 30 days or the aggregate history since the beginning of the survey of what I'm looking at. And so what we're finding is that our data archives are actually getting hit by millions of queries a day, both by ourselves and by communities, for data to say, okay, this changed last night, but what was it doing a week ago, a month ago, a year ago? The other thing is that those alerts only give you a 5 sigma change because it's coming from difference imaging. And there's a lot of the sky which is changing on slower, lower sigma variability that you're not getting in the alert stream, that you only detect when you get one of the data releases and do an archival trawl back through the history to see what has changed. And that's important for a lot of phenomena. There's a lot of slow phenomena out there that 5 sigma is not going to get you. And that's also going to be a problem for LSST. And you see, I think we're going to see the buildup of large sentinel or large watch lists for doing photometric monitoring for variable sources rather than just the supernova or the tidal disruption events or the solar system objects. And this is important. The history is also important for the rates of particular transients. One of the other things we're seeing is that we originally had this idea that there would be different components in that brokering infrastructure and how the time domain infrastructure would work with marshals, with brokers, with repositories, with the TOMs that are coming online now to manage the follow-up observations. And what we're beginning to see, I think, is a lot of those are all being folded into single data management systems that various groups are putting together. So we're seeing sort of one-stop shopping, or we're seeing super apps or something like that. Even within ZTF, we have a new sort of super marshal called Fritz, developed by Dmitry Duev and Josh Bloom at Berkeley, which is integrating a lot of this infrastructure together. So it has a very powerful data management backend with all the archives there, but also allows you to do filtering of event streams. It allows you to do searches. It allows you to trigger stuff off the telescopes and whatever. And I think that's maybe something which is a little surprising. We thought we would see a more decentralized network, and that's not what we're seeing. It seems to be that people want a one-stop shop for managing the alert streams in the community usage. However, I think that the model we presented back in 2008 and the model that has driven a lot of the development of what's going on in the community has some misconceptions or some misperceptions. As I say, there's this idea that, back in 2008, we were saying you will need one of the top 1,000 computers to manage LSST. You will need the top computer to manage SKA event streams. This idea of having these super cloud resources available to you is sort of quite clearly wrong. Networking, that I need to be connected to the fire hose. I need to be receiving millions of alerts a night directly. This idea that I need to persist everything locally, because I can't trust community stores or data stores out in the archives, I need to have my own local copy, and everything I receive, I need to persist. And the danger here is that we're going towards these ideas of the super app then becomes a monolithic thing, which controls everything, becomes more complicated, and then we are bound into those systems as we go forward. But I think what we're also seeing is we're seeing an evolving landscape. Back in 2008, we had this idea of working with alerts. The alert landscape should be broker-based, and that was to manage the volume and velocity of alert data. But we don't need those systems. And we're now seeing a transitioning to more general systems in the community that are not just working with alerts from transients, but are working with variable sources, that this is becoming a more general time domain environment. And we've got new use cases coming that people want to be working with the alert, but they also want to be able to handle the light curve, the SED, all as primary data objects rather than ancillary data objects that are done downstream processing. Veracity is also becoming increasingly important. I'd like to know what the provenance of what I'm doing, the provenance of the data I'm receiving, what has been worked on it already, that sort of thing. So I think what we're seeing is a transition now from data management systems with the alert streams actually into information management systems, where we're trying to put this all together and combine it. And I think that's a slightly different landscape from what we were looking at. I think one of the ways we can make some great inroads into that is actually to decentralize and look to the Internet of Things. So this is your smartphone, your smart fridge, your smart microwave, your Alexa system at home. And one way that you can do it is the artificial intelligence systems that are making use of that are looking at hardware accelerators for doing inferencing. And this is the so-called edge TPUs. And we can demonstrate that on a simple USB plug into a Raspberry Pi, you can process a night's worth of ZTF alerts in 5 minutes or less than 3 minutes this year. So if you're looking to do really fast AI inferencing, which is probably what you need to do a lot of the classification, the characterization that you're interested in working with these data portfolios, you can do this much more efficiently on these very lightweight, low-cost systems that are improving month by month. Just last month, Coral have introduced a new dual TPU board, which gives 8 TOPS as the processing speed, which is slightly bigger than a US quarter. So we can have these systems for low cost, which could handle a lot of the computing, and with smart networking and such, we can sort of do it. The other thing that this sort of model allows you to do is actually federated learning, where you bring the model to the data rather than the data to the model. So in training these sorts of things, I don't need to have a big GPU cluster. I can do it on the edge, and I can make use of local data, local heterogeneous data, which maintains data privacy. So it maintains access to proprietary data, if that helps. And the only thing that is then exchanged with the central server is the weight of the updated model. So all specific local learning contributes to global learning. So you've decentralized the learning of your AI systems as well. And I think that's where we need to be thinking and heading towards. So a vision for 2030, I think in comparison to where we were thinking about in 2008 with this environment of data streams and such from Sky surveys, it's no longer about volume, velocity, and variety of data, but it's actually it's going to be about information and knowledge management. And I think we're not going to be working with static classifications, static quantities. With the rise of even more AI systems coming through and more astrostatistics coming through, I think we're going to be having a much more fluid environment where we're going to be working with dynamic probabilistic quantities, where veracity is actually going to be extremely important, because you're going to want to know exactly what version of what produced the thing that you're looking at in terms of doing your inferencing, and what are your priors and where are they coming from. Centralized systems in that sort of environment are cost and energy inefficient rather. And I think that energy inefficiency is going to come up as well. To train these big data, these big AI models is very costly in terms of energy. So I think in 2030, we're going to be looking at decentralized intelligence networks running on these low cost components, employing commodity hardware accelerators and reusable models, where you can just use transfer learning on the edge to improve, and you get response time and save bandwidth. And so I look forward to giving a talk at ADASS 40, where I can reflect on the predictions I've made today and the environment we're looking at and see where I got wrong. So thank you very much.
Many thanks, Matthew. So yeah, let's see. So for sure, we will all want to hear again in 12 years' time or in 10 years' time. So there are a couple of questions in the Q&A, and one also in Discord. So the first one on the Q&A is, what does ZTF report to TNS?
So ZTF has, there is an automated system. So there are two reportings going on to TNS. The Alerse broker, which is an external entity to ZTF, reports supernova, early time detections of supernova based on single alerts to TNS. ZTF project itself, we have the Ampel broker from the DESI group in Germany, which has a number of automated filters on the alert stream, and high probability candidates for supernova in both TDEs are reported that way automatically into TNS.
Okay. There is another question from Thomas in Discord, which says, you said that we do not have enough confidence in machine learning yet. So what is your opinion on why that is?
I think the problem is that we are still, scientifically, we're still very much in the mindset that everyone's looking for the rare objects. And so therefore, we're doing individual object studies. We're in an industrial alert scale mode, and we're going to be even more so with LSST. And I think somewhat conceptually, we haven't made that transition yet, where we can be very systematic and look at populations of rare objects. And, you know, if you've got 1 billion sources, that's going to give you 1,000 1 in a million detections. And we're all still looking for the low-hanging fruit, but I think we need to move into this idea that the outlier detections, the anomaly detection systems are good enough to find those rare things. And you can demonstrate that through, you know, take a training set and build one and see what you would find if you went through it and see what the system will find. And I can tell you that the AI systems do better, but there's a lack of trust in it for some reason. There's still this big scare that we're going to miss something, or that we're going to turn some follow-up facility onto something that turns out not to be real. But I think, you know, our false positive rates are such that that's very unlikely to happen, and going to improve even as we go further. So I think there's a scientific change that has to happen, that we should trust these things, and we should be happy that these things are looking at the data and trusted, rather than, you know, you need nightly or daily grad students to review thousands of alerts looking for supernovae or something like that.
Okay. And what do you think will be the trigger that will bring that change?
Hello.
I think it has to be. LSST turning on. I think once you start getting, you know, 10 to 40 million alerts a night, what we've seen in ZTF, there has been, for example, in the solar system group, they were quite happily scanning very many thousands of alerts every morning looking for moving objects. Then we brought in a new machine learning algorithm, which reduced that down to a few tens every morning. And so people now trust that the deep streak system does a very good job in classification. I think when you're dealing with, you know, having to look through 100,000 alerts every day to find a supernova, you're not going to do that. No grad student's going to do that. No team of grad students is going to do that. And just the economy of scale is going to be such that you have to rely then on the AI systems to do it for you.
Okay. So in the Q&A, not sure it's a question or just a statement, but maybe you want to comment on that. From Anno saying 300 million alerts, that's a high percentage of false alerts, it seems.
No, it's not a high percentage of false alerts. It's what you've got to remember is that there are a lot of variable stars in the galaxy, and we scan the galaxy, we don't miss it. So variable stars, variable phenomena produce alerts just as much as any supernova or tidal disruption event, or, you know, some explosive eruptive or thing. It's just a 5 sigma change in the magnitude or the position relative to the reference image. And so for something that's bright, it doesn't need to change by much to generate an alert. So if you think these are all from transients, then that's a misperception about what you're seeing in the alert stream.
Okay.
But we have a very good, again, our real bogus machine learning has a very high very low false positive rate, very high true positive rate.
Okay. The question from Simon: how difficult is it to program a TPU compared to, say, a GPU?
It's trivial. If you use Google Colab, you can actually get experience with working with a TPU. You can just select it as the hardware accelerator you want to use instead of a GPU for training. So TensorFlow and all those libraries for working with machine learning will do it for you. With using the hardware accelerator itself, the HTPU, you just have to you have to convert your model from TensorFlow to TensorFlow Lite and then port it. But that's something that the TensorFlow libraries do for you.
Okay, many thanks. So, okay, I think we are just spot on. So many thanks, Matthew, for this great talk. And yeah, we meet again in 2030, where I hope much before, but
yes, indeed.
Okay, so many thanks, Matthew. I think now we are having a break of 15 minutes, and so we have the time to have a coffee or whiskey, depending on the time of the day, and then we see each other in 15 minutes. Okay, so I think we've done the test with Fenya already. So this worked fine. Vicente, did you want to do a test? Yeah, so Matthew, maybe you need to stop sharing.
Can you hear me?
Yeah, I can hear you.
I have stopped sharing.
Okay, thanks. Yeah, all right, yes. So Vicente, if you want to give it a try.
So I'm going to try to prepare several things here. So I will start my video as well.
Yeah.
Hello. Can you see me?
Yeah, perfect.
Good. Okay. And then, so you can hear me, you can see me, and now I'm going to launch my presentation. So the screen, the entire screen, screen one, share.
Yeah, just put it in full
Yeah.
in presentation mode, so just to make sure. Yeah, so that's
How about now?
perfect.
Okay.
Okay.
So you can see me, you can hear me, and you can see the presentation, and it works.
And if you can put a timer on your mobile next to you, I think that would be useful. I'm going to say that.
Sorry? Say it again?
If you can put a timer on your mobile next to you.
Yeah. It's already there.
Okay. Okay. Excellent. Okay.
Is there anything that I cannot see myself while I'm speaking, but okay, I guess it's okay.
No, sorry, we can see you while you're sharing the screen. We can see you.
You can, right?
Yeah. No. Now we can now maybe your camera is off. Yeah, now we can see you.
Now
yes.
it is. Okay.
Now it's fine.
So now you can see my screen.
Yeah.
And now I guess that you
on you. So it's all fine.
Let's go into, you can still see me, right?
Yes. Yes.
Okay. Everything is working.
Very
Okay,
good.
thank you.
Giuseppe, do you want to give a try? I see you online.
Well, good morning. Can you hear me?
Yes.
Okay, see my video and let me share the screen. Work. I share my screen. Can you hear me?
Yeah, we can hear you, but I can't see me. Probably.
It's strange because for my side it works. Can you see my desktop?
Okay, now we don't see anything. Okay, now it's coming. Yeah, we can see, we see, I mean, I see myself.
Okay, let me.
We are seeing your desktop, but you are sharing the video of Zoom, so we are seeing the person on Zoom, who is Christophe.
Yes.
Okay, so problem from my side, I am not able to share the screen, but it seems to work.
But can you share, I mean, maybe you need to start your presentation. Okay, now we see you. That's better.
Okay, so schema.
Now we still see the Zoom main panel.
Okay. Let me close and reopen. Sorry.
Okay. Mario, do you want to give it a try in the meantime? Mario has gone.
Yes. Can you hear me?
Yes. Yeah, we can hear you and see you fine.
All right. So let's try this out. So you should be seeing my desktop now, and here's the presentation.
Perfect. Yeah. Excellent.
Good. All right. And just let me check one more thing, because I'll be doing a demo. So just make sure that. Can you see a web browser window now?
Yes, it's maybe not full screen. Maybe you can put it on.
You think this will be better?
Yes, that's much better. Yes. Yeah,
Okay.
it is better. Yeah.
Sounds good. Looks like it'll work. Thanks.
Excellent. Thanks, Mario.
Okay, let me try. It's Giuseppe. Let me share the screen. Works. I share the screen from my site.
Hi, Giuseppe. I think you need to minimize the browser and then open your presentation so we can see it. Okay.
Yes. Now it's better.
Yes.
Yeah.
Yes.
Oh, okay. Many thanks. Okay, sorry.
Okay, now it's perfect.
Yeah, that's perfect.
Okay, thanks.
But
Thanks,
we
Anna.
don't see
Thanks,
you in the video.
Okay.
I'm confused. When is Giuseppe in the program? For which talk is he?
So it's the third one. So we start with Fenya, then Vicente, then Giuseppe.
Oh, I need to reload my browser, I guess. Okay.
So we have 3 contributed talks, and then we go to the focus demo.
Okay, I had an old schedule. Sorry.
Me too.
Okay, I'm just
want to try the. Sorry.
I'm just looking at the web page. Yeah.
Peter, do you want to try the spotlight with the video?
Yeah, let's see if that works for me. Who should I try in Spotlight?
Okay, I put my video now. Christophe and I are live.
All right,
so you can choose between us.
Yeah, I only see 6 options. Stop video, change role, don't allow to record, rename, put on hold, remove.
But can you try it in the, not in the participant list, but in the video? Can you see our videos?
Yes, I see the little video icon, but when I click on it, I only see 6 options. For Christophe, for example, when I click on somebody who is not having the video on, it says ask to start video, but that's it. I do remember when we did the training, I saw it, but not today.
Yeah, well, yeah, I don't know. Well,
okay,
I can take care of that. Yes,
you're here too.
It's weird, but I do it.
It is weird.
Yeah. Okay. No problem.
So for all the speakers, so it's a 15 minutes talk, so which consists of so 12 minutes for your presentation and 3 minutes for questions. So maybe what I'll do is a couple of minutes before, around 10 minutes, I will just switch on my camera again, so you know that yeah, there are 2 minutes left. But if you have a timer next to you, that would be even better. So it's less intrusive. Because it's not easy to to make sign remotely. And if you want, Svenja, if you want to start setting up your, the screen, so then, well, we still have 5 minutes ahead of the session, but as you're the first speaker. Fenya, so do you want to start your video on the screen, start sharing the screen?
As I said, I'm not going to start to share the screen, but I'm going to start my camera.
Ah, yeah, true. Yeah.
So you can see my slides right now. So that's correct? Yeah,
it's
lovely.
Okay.
And this is exactly how it's going to stay, just the whole time the video stream.
Okay, fine, good.
Wir sind soweit. Weniger Blende, ja.
Wunderbar.
Wenn du on bist, sagst du es Bescheid. Ja?
So, Fenya, how do you pronounce your last name? Just to make sure I pronounce it properly.
It's collage.
Collage, okay.
Exactly,
Fenya.
yeah.
Okay, Fenya collage. So now we see you, huh? We don't see the screen. Ah, and you're muted, but okay.
Du kannst doch mal sagen.
Ja.
Genau.
There is a bit of echo. Okay. Okay, so welcome back everybody. So for this session, so we are going to start the session with Fenya Kolash. She's a master student in applied computer science at the University of Heidelberg and a student researcher at the astroinformatics groups in HITS. And she's going to speak about the Explorer toolbox for exploration framework for big data set. So Fenya, the floor is yours.
Yeah, wonderful UTC morning to everybody. Yeah, I'm going to tell you about the idea of an Explorer's toolbox, what all of you data adventurers need when you went through all the jungle that is currently very large due to the huge big data issues. Just a very quick reminder, I'm here at the Heidelberg Institute for Theoretical Studies with a very professional filming team. So everything you're seeing right now is streamed via cameras. I will not share my screen. Please don't force me to share my screen because this will probably cause to collapse everything. Yeah, I'm starting with a very basic issue, not even only in astronomy, but in all kinds of data sciences by now. The amounts of data that we are dealing with are getting larger and larger over time. And this is by far no new topic. And I think even alone in this week, you heard about this issue about 100 million times. Just to give you an idea about if this might be still something new for you, I displayed this table with data from 2017. Just to have a brief idea about how big the largest sky surveys are over there. And the data I display here is actually quite outdated. So by now we are not even dealing with terabytes and petabytes, we are dealing with larger spaces with zettabytes, and it's not going to be any better. It's getting worse and worse every day. There's getting more data. And this causes you as an innocent researcher to get lost in this whole forest of data point trees where no escape is for sure. So this is why machine learning became a huge trend in astronomy, in molecular biology, in basically all data sciences by now. We hope that our Lord and Savior machine learning will come to our rescue to help us to get an overview about all the data, to outsource tasks that are cumbersome to do and that are hard to do by hand if you're dealing with such large amounts of data over there. And this sounds very beautiful every time because it looks like, oh yeah, this is like I take my huge unstructured data, put it in and get my solutions out and get directly my research thesis and go to Stockholm to get the Nobel Prize because I made an awesome, an awesome contribution to research. But the reality, as you might know, as everybody knows that worked with machine learning, looks a little bit different. It's not like you change your rusty bike into a fancy sports car and drive all the way to Stockholm. It's more like, okay, you start questioning yourself, what exactly do I want to show with my data? What do I want to do with my data? What am I looking for? Then you start extracting the appropriate data for this and fall into a whole pit of stones because you see this is very, very painful to get all these data. And if you finally got out of this pitfall, got all your data, you have to start cleaning. And this is what I introduced very briefly in the beginning. It's looking like you're in a giant forest with many, many trees, and you don't know which trees you want to cut down or something. If you have done this, you realize that all your nice cleaned data isn't compatible to the algorithms you want to use or to the programs you want to use. So you have to build a bridge to make data integration. What follows is a very, very awful journey across a stormy sea with a nutshell, sort of, because you see that the data has faults, that they are missing values, that you need to patch something up. And after you made feature engineering to actually made it at least a little bit usable, not only for you, but also for other people, you find out that all your models are completely garbage and you start to evaluate them. You have to crawl out of the last pit. But after that, you finally have a result. And yeah, this complicated journey, this rocky road that you have to go in machine learning is, for someone like me as a software developer, something that I think this is not okay. This makes this wonderful solution for the big data issue very unattractive for researchers that maybe are not familiar with computer science, that maybe are not programmers, that they just want to do their research. And they see this complicated road and think like, yeah, okay, whatever, I'm still doing this all by myself. I'm still doing this by hand because this is even easier than going this road over there. Like I said, this is where I want to come in to make this whole process at least a little bit easier for all of you, a little bit more usable. This is where software engineers speak about usability. We need usable machine learning programs. We need usable frameworks for you researchers to work efficiently. So how could such an exploration framework, such an exploration program with a nice usability look like? And to evaluate this, I want to talk a little bit with you about how we explore data and what are the important points from a software developer's point of view. So as I stressed out, we have to focus on the problem that we don't have to get our data explorers get lost in the data jungle. Basically, what they are doing is they perform distributed over many, many different types of data, many different data points like images, like curves, like tables, like plots, all over very different possibilities to visualize this data. But while they explore, they're basically performing the same actions. Yeah, you usually are browsing, you are scrolling through data, you are looking for something, you are filtering, you are doing different tasks for sure, and they have to be realized in different ways, but yet they are more or less the same tasks. And this is where software engineers are always like, yeah, nice, let's make a pipeline to organize these actions. The reality of this idea is perfectly described by this XKCD comic down below, because this usually looks like, hey, awesome, I made a wonderful automated data pipeline that processes everything automatically. And the reality is like, okay, this is a giant pile of random scripts that just explode if you input anything that's weird. So how can we solve this issue? How can we try to make a pipeline that will not explode if you do something unexpected at this point? And this is where I want to stress out that we have to keep pipelines, that we have to keep frameworks that want to make this easy for researchers more generic than by now. Now the state of the art is we have specific programs for specific issues that only work for this current issue and are completely going bonkers if you do anything with it that it was not meant to be for. Why do I think this could work? To display an abstract application is always a little bit difficult, but the two core aspects that influence the user experience during data exploration, these two aspects are very abstract, because this is for once visualization. Yeah, you need to have a visualization of your data. You need to see what you are looking for. Vision is the human's most strong sense. And you need to interact with this data. And by the visualization, this is where we actually get to our first issue, more or less, because visualization is a very complicated process itself. This is why I displayed the visualization pipeline on top of this. So you almost halfway go through your data exploration just by finding an appropriate visualization. And this is leading to the fact that the applications are, again, very, very hard to make abstract, very much tailored to a specific problem. This is why I took the freedom to derive from the visualization pipeline a sort of exploration pipeline, where I think, yeah, of course, we need these points like pre-analysis, but we don't have to do the pre-analysis by ourselves. Let machine learning do the pre-analysis, but let the researcher decide which machine learning algorithm he wants to use for this. You need a mapping to a visualization, but let the researcher decide what kind of visualization this should be. And this is not the end of the road, by far not, because this is when the fun actually begins. Now you can efficiently explore your data, and this happens about interaction. So it's very important that we have a visualization that is interactable at this point, where you can click on the data, where you can enlarge, where you can zoom, all these things. And this is a process that repeats and repeats and repeats until a point where you finally found something that is interesting. To make this possible, we need abstract data types at this point, right? Because how you interact, this is definitely specific to your apparent problem, but that you have to interact, that is clear for all types of data and all types of explorations. So we need an abstract interface for these interactions and for the visualization. And why I believe this is working is because interaction is on a computer program that shows a visualization, nothing more than spatial transformations. And maybe you followed the talk that I gave, or the poster that I made 2 years ago, where I talked about spatial transformations in astronomy. This is something that is realizable in an abstract way. Just to give you an idea how such exploration frameworks look like, I present you very briefly 2 prototypes. The first one is the MegaVis prototype to perform dimensionality reduction on spectral data in order to display them in 3D. So this happens by training an autoencoder, using the latent space of this autoencoder to be actually visualized. This looks like this. So in the diagram, you see the latent space of an autoencoder that was trained with spectral data. This is a very, very nice prototype developed by Antonio de Santos, who also works in my group. And if you now click at one of these points in the latent space sorted by similarity, you can see for once the prediction of the autoencoder itself, the reconstruction of the original spectrum, as well as the closest original spectrum that fits to this prototype at this point. Or maybe you remember the last ADASS in Groningen, where Bernd Doser and I presented pink and ultra pink, also 2 applications from our research group. So pink is an application where you also do dimensionality reduction with self-organizing coordinate maps, where the common shapes in the data set are represented by a certain number of prototypes. And I contributed a front end for this pink framework that you can actually see the prototypes, see the self-organizing maps, and interact with it. And this sort of looks like this. So here you see such a self-organizing map on the Radio Galaxy Zoo dataset, for example, with 4 times 4 neurons, 4 times 4 prototypes. And now you have the possibility to explore these prototypes, these representations of the common shapes in the dataset, click on them, zoom on them, select them, label them, even export them. You can have a view on the 10 best matching fits, so the real data, the best 10 real data points that fit to a certain prototype, for example, and many, many more things.
A couple of minutes more. So
Thank you so much for that. I told you about generic frameworks in a very, very long monologue, and now I presented these 2 prototypes, and now evil tongues will say, yeah, these are not generic at all. These are specifically tailored, as you said, and you were talking about this is the problem. That's right. These 2 applications are still not abstract, but we hope to make them such a thing. We hope to combine not only UltraPink and MegaVis, but there are so many interesting approaches to make frameworks for visualization and exploration. Alone in the last days, I saw very, very interesting presentations about pipelines and about frameworks. I saw even a very nice tutorial on Sunday from Peter Williams about exploring the WWT data. What we like to have is one framework working on abstract data types to be usable for all different kinds of data, that you don't have to reinvent the wheel all over the time again, that you really have a nice framework with a great usability that helps you to explore your data and don't lose the focus on your research by having to deal with annoying problems in the data processing. Thanks for the ability to talk over here. Hit me up on Discord if you have any questions, or maybe you even want to check out my GitHub repository. I would really like to say you were a great audience, but actually I have no idea. But at least I hope so. Thank you so much, and yeah.
Thanks a lot, Fenia. So yeah, I think we will, as you suggested, maybe if people have questions, I'll suggest they put them in Discord, and then you can answer them directly. There are no direct questions now on the, I think we should move to the next speaker. But thanks again, Fenia, and then we now move to Vicente.
Hello?
Yeah.
Okay.
Okay, so yeah, Vicente is a system engineer on the data science principle at ESA in Spain, and is responsible for the development of operations of a science grant segment. And today he's going to speak to us about ESA Data Labs, the science platform for data exploitation and preservation at ESA. So Vicente, the floor is yours.
Thank you very much, Christoph. Good morning, good afternoon, good evening, depending on your time zone. I hope you are enjoying ADASS. This is special ADASS. Today I'm going to give talk about ESA Data Labs, a project that was formerly known as ESA Science Exploitation and Preservation Platform, but we think that this name conveys quickly the message that we want to transmit. Actually, this was a name that was used yesterday in a presentation provided by Vandana Desai on the subject. So we have branded the project. So let's go into. Okay. So the project started, we could say that it was kicked off in 2017, and it was kicked off with several projects in the background and a discussion that we had with many of the missions that we have at ESA in order to combine the two mindsets that are defined by the different styles of these missions, whether the missions are in legacy, operational, in development, and so on and so forth. So depending on the status of the mission, you have an exploitative view of the problem. So you want to address your operations and the present problems that you have. So this triggers usually incremental innovation. And the explorative mindsets of the missions that are in development or concept are usually triggering this kind of disruptive innovation that we need to fulfill their needs. So combining these two mindsets, we try to address their needs, and we identified three main drivers that have been the main goals that we've been addressing with ESA Data Labs. So let's have a look at these three drivers. On one side, there's big data. We've been talking about big data for quite a long time, but it's clear now that the amount of data that we are talking at present is really becoming big data. In the past, there was a little of discussion whether this was a hot topic and a real topic. And now we can see here on this slide on the left an image that you may have seen already in past presentations also from ESA. Yesterday was a presentation from my colleague, Marcos Lopez Caniego, who presented the same kind of slide on the Space Science Archives, where you can see the evolution that is going to be triggered by the new missions, and especially Euclid, which will boost our Space Science Archives volume by around 20 petabytes. And then on the right-hand side, you can see one experiment that we are running at ESAC, which is called GNSS Big Data. That is a special GNSS station that is capable of recording all the intermediate frequency data that is generated by the GNSS signal, which is usually discarded because we are focused on extracting the main products that are basically based on positioning. But if you want to do the science with that signal, and you want to uncover the golden nuggets that are embedded in that signal, this is an excellent instrument. So what this has confirmed, as we have seen in this ADASS conference and past ADASS conferences, is a clear change in the paradigm where we need to move from the data transfer to computation to a new paradigm that is based on the computation transfer to the data. So that was the first driver. And then the second driver was, okay, we need to make use of these innovative data analysis tools that we are provided. And of course, more in particular, the artificial intelligence, machine learning kind of data analysis tools, advanced analysis tools. The position here of ESA Data Labs is, you can see on the top of the slide, the reference to, well, this is based on an article that shows what is the weight or the participation of the actual machine learning code compared to the surrounding infrastructure that you need to run this machine learning code in operations in development. Okay. So what we are aiming here is we are aiming at protecting the data scientist, which is in charge of the model development, who is developing their models, machine learning models with the tools that are more interesting or more easy to use for the data scientists. Let's say TensorFlow, PyTorch, Scikit-learn, RStudio, you name it, JupyterLab, which is omnipresent everywhere. So data scientists can focus on that. And all the complexity that you can see surrounding this machine learning code will be delegated to a complex IT infrastructure that will be hidden from this data scientist. So on the other side, you have a different set of expertise like Amazon Web Services, Spark, GPUs, TPUs, Docker containers. In the past, the original data scientists had to kind of control everything. Now, what we are trying to do is we are trying to make this transition to machine learning more effective so that you can focus on the real stuff. And the other thing is that we wanted to move into collaboration, but not collaboration in the shape of sharing things. We wanted to drive ESA Data Labs towards a citizen science, open science perspective so that everybody could contribute and basically benefit from the archives. In this case, we wanted to break the silos that we traditionally have in the archives, where you go to the scientific archives, the navigation archives, ops archives, Earth observation archives. So we wanted to also bring collaboration across different domains so that you could enable different type of science that benefits from findings and data sources that are provided by other areas of the agency in this case. So here you can see at last the homepage of the Data Labs ESA portal. Just a warning, we are still, if you go to Data Labs ESA Int, you will see that it's still not open. What I'm going to show to you is today is present are snippets from our development and integration environment that is almost ready, and we plan to open in Q4. On the right-hand side, you can see basically that this is a really multidisciplinary exercise where you need to combine in a single team all the different skills that are required to build an infrastructure as a service, a platform as a service, and a software as a service. So being software as a service, the area where the scientific work is carried out, and then all the platform as a service and infrastructure as a service combines these IT engineering teams that are specialized in big data, in deployment of machine learning models, and scalability, and so on and so forth. So let's have a look at ESA Data Labs as it is right now. So you can see here a screenshot from our system. And the first thing that you will see if you go into ESA Data Labs is that you will be able to go into our Data Labs catalog, where you will find a different set of pre-configured data labs that you will be able to activate. So here you have an example of all the different systems that we have right now in our integration environment. We'll go a bit more into the details. So at some point, you will realize that there's a pretty high number of data labs that are already provided by the infrastructure. So we have this search functionality where, in this case, I went and I searched for lab, and then I got all the lab, in this case, Jupyter labs that are available, and also some desktop applications, this GNSS lab tool that is also using the lab concept. So you can see here Jupyter labs provided by our ESDC team at ISAC, Euclid mission, Hersen mission, Interval, so on and so forth. So launching the data lab, once you have reached that point, is as easy as just clicking on the lab and say launch it. And you can see in the bottom part of my presentation the dashboard that at that point in time I had running. So these are all the labs that I launched for this demo, and they were all running at the same time in the ESA Data Labs environment. Okay, so eventually this dashboard will take me to all these different data labs that are running in parallel, all of them providing functionality for different areas and data labs that I am interested in, and sharing the same infrastructure. So you can see here examples from data labs that are using ESA Sky, that has also been mentioned by my ESA colleagues. Some ESA data labs that are on the right-hand side. At the bottom, you can see an ESA data lab that was also presented last year, doing some clustering analysis with HDB scan libraries, and so on and so forth. So, but ESA data labs, we were talking about bringing the code to the data. So this is actually what you can do with ESA data labs. You can access our ESA archives, but not only the ESA archives, you can also access private areas and more. So what you can see on the left is that there's a special area for the users, 10 gigabytes of data, more or less, that is available for the users to put their own data and access their own data close to the ESA data labs. And on the right, you can see the data volumes that can be mounted on the ESA data labs, like ESA data volumes. You can see here Gaia as one of them. And there are also data labs using Planck and so on and so forth. So the heliophysics, astronomy, and planetary archives can be mounted into ESA data labs. And finally, you can see these more things that are basically possibilities to use these social tools that we are all used to use, like Dropbox, Amazon Drive, Google Drive, and so on and so forth. When I was talking about the notebooks, the special thing about these notebooks is that they are all pre-cooked and pre-configured with the AI packages or the mission-specific, domain-specific analysis tools that we want to use. And you can see, for example, in this example, there are different notebooks that are offered by the different missions. And this is an excellent way, as we have discussed in previous presentation, to get familiarized with the tools that we are using and provide examples of how to access our archives. And on the one side, we have the web-based tools like Jupyter Lab, okay? But at the same time, ESA Data Labs provides the possibility to access desktop applications that are full-fledged applications that provide access, like, for example, Topcat that we can see on the left, or legacy applications that we've been using in the past for the data analysis of the missions, bringing this possibility of data analysis tool preservation. That is one of the other objectives of ESA Data Labs. So very quickly, this is the technology.
Vicente, 2 minutes.
Yes. So this is the technology stack of ESA Data Labs, just to give you an idea of where the data analysis is in the middle, and then the surrounding area that is all the functionality that we have in ESA Data Labs. So what's next? Next, we are delivering on this advanced data analysis functionality. So we are deploying inside ESA Data Labs functionality to combine those data labs into a workflow and eventually support the possibility to create machine learning workflows. So this is a generic functionality for pipeline management and a complete functionality for machine learning workflows. So we aim at providing support for the blue boxes that you see on the right that are going beyond the data preparation and the code modeling that is to be provided by the users. So you can see here the future blueprint of ESA Data Labs. The most interesting aspect of this slide is that we are aiming at providing ESA infrastructure for ESA Data Labs, but we are also considering to extend ESA Data Labs with infrastructure that will run outside ESA for scalability purposes. So if you have an account in Amazon Web Services, the idea would be that, or Google Cloud or Azure, you can go and leverage on those resources, sending your data labs to them. This will be the snippet of the future integration of the archives into ESA Data Labs, so there will be links to ESA Data Labs in our future archives. So the conclusions. So basically, ESA Data Labs is ESA's answer to the paradigm shift that we are observing to serve the big data wave. There's it's an environment for a scientist, designed for a scientist. The objective is to make science easy, not to drive complexity to the scientists, so that they need to become aware of all the complexities to run a machine learning model, for example. It's an open environment, so promoting citizen science. It's not just for the core users of the missions, but also open to any other users outside the environment of ESA. And then this is the last statement. is not a check, because for this I think that we need the support from all of you. The idea here is to open the possibility for the data labs to go to other environments. It's clear that we are not going to be able to have all the data in a single place. So here I want to open the door and call for action in order to try to collaborate, in order to be able to send our data labs the same way that we could send them to Amazon Cloud, we could send them to other organizations. So bring your own science to the organization that you want. So that's it. That's the end of my presentation. So if you have any questions, in the pleasure.
Thanks, Vicente. I don't see any specific questions, but I have one also a bit following what was discussed yesterday. So there are now several science exploitation platform or science platform. How do you think we could connect them?
Yeah. So this is exactly my last point, where I was saying that we need to talk and we need to coordinate in order to make this possible, because I think that this is the next step. And actually, when I was referring to this last point, I was thinking, getting inspired by the gaming world. I don't know if you are familiarized with platforms like Google's Stadia, or more concretely, for example, GeForce Now. And that's the reason for me, my eScience Now or PlayStation Now. So the concept of these environments, and they are commercial, is that basically you create these games and you have these app stores for the games, and you can run those games in the infrastructure of, in this case, NVIDIA. Okay. So basically you have the game stored in one place and you want to play with that game in another infrastructure. And they are containerizing these games, so they become our data lab, and you can send them to other places. So in order to, it's not a technical problem, in my opinion. It's more a coordination problem to start defining, as part of ISA data labs, we are trying to define the metadata that will surround our data labs. And I think that within the IVOA, the Virtual Observatory initiative, there could be maybe a group that could discuss how to containerize data labs, or you name it, science apps, astronomy science apps, in a way that can be forwarded to other places, because it's clear that the data, as it was also mentioned yesterday by Bandana, it will not be possible to have everything in one place.
Okay. Okay, many thanks. I mean, there are now two questions coming, but I'm afraid we will in the Q&A. So I think we should move to the next presentation. But so Vicente, can you maybe answer the two questions in the Q&A? Answer them in the either in the Q&A or in Discord.
Yes,
thanks
sure.
a lot.
Yeah. Sure. Thank you very much.
Thanks a lot, Vicente. Sorry for Laurent and Marc, but so the next presentation now is Giuseppe Greco.
Hi, everybody. Can you hear me?
Yes. So okay. Giuseppe has been working in the context of multi-messenger research, developing practical tools in the context of various European-funded projects. So yeah, Giuseppe, the floor is yours.
Okay. Many thanks, of course, to the organizers to design the wonderful online ADASS meeting. This is my first ADASS conference, so I am very happy to be here. Well, in my talk, I will focus on the capability to describe the gravitational wave scale localizations using the so-called multi-order data structure. It's a quite large research program. Today, it's a support from two main European projects, and they are ESCAPE and AHEAD. In particular, the last one is mainly designed for high energy emission. I divided my talk into three main parts. Firstly, a very short introduction to the GW scale localizations and the last results from LIGO and Virgo. Then I will show you a few practical examples and applications in a real context. And finally, I will discuss the benefit to encode the space and time simultaneously, the so-called space-time mode. And by looking for the future, I will try to figure out any possible applications for the next generations of interferometer, Einstein telescope, the ET observatory. Well, most probably the next observational run from LIGO, Virgo, and Cagra at that time will start at the beginning of 2022. All sky maps will be issued in the multi-order format. Multi-order is developed by Leo Singer, and here on the top of my slide, you can find any resources from LIGO and Virgo user guide. Multi-order is supported from several tools like .schemap, AstroPy HeatPix, MockPy, and the last version of Aladdin version 11. So mock and multi-order are closely related, of course. Multi-order encodes probability map, that means probability density, distance estimations, while mock maps regions with no value attached. More specifically, mock is an efficient method to encode the complex region over the sky using predefined cells. Each mock cell is defined by two numbers, the HeatPix order and the HeatPix IPix. Of course, mock is based on a HeatPix tessellation of the sky. The Unix scheme defines an algorithm for packing order and IPix into a single integer usually stored in a single column fist table. The mock algorithm is developed by Fernick and collaborator in 2014, and today it is supported from the International Wind Observatory Alliance. Well, here in the animated GIF, you can visualize the last LIGO and Virgo catalog from April to November 2019, the first part of the observational run number 3. For that reason, O3A. 39 events are observed, and it is quite clear that the GW sky localizations are characterized by regular areas, and only in a few cases you can apply, for example, an easy fit ellipse mode. Well, it's very easy to encode with mock the GW sky localizations, as in the GIF. You just needed to get the probability list from the HeatPix file, to sort it in the descending order, and sum up the pixel values in order to get the confidence level that you wish. Finally, from such pixel table, of course, you can apply the mock encoding. In particular, the methods implemented MockPy calculate the integrated probability by dividing the last pixel at the lowest resolution presented in a multi-order format discussed before, the official LIGO and Virgo format for the next observational run. Well, I think it's very interesting to stress that mock meets a very large support from the community, a very large community. And I think it's a good news for the researchers involved in the EM follow-up of gravitational wave events. As an example, you can write a Jupyter tutorial using the iPaladin widget. MockPy is an affiliated AstroPy package, or just you can build the incredible region with Aladdin and query Vizier from mock. So let me show you a practical application. Here an application from the Engrave collaborations using MockPy and the matplot library in Python, of course. The plot shows the EM follow-up from ATLAS, VST, Pan-STARRS, GOTO, and VISTA telescopes. You can visualize the line inference schema and 19, 50, 10% confidence levels, and the initial bias star schema in light gray. It's the coverage of the GW event 190814 and published by the Engrave collaboration in the Astronomy and Astrophysics. Again, you can interactively visualize in Jupyter sky localizations at different confidence levels as independent planes, as you saw in the video. You can download and run the tutorials from the link reported in this slide. Again, you can interactively visualize different sky maps issued for the same event. In such example, you see the sky localization of GW 19814, the initial by-star sky map, the initial line inference, and the final sky map published during the summer and a few months ago. Well, you can do more. You can measure the intersection from two or more sky maps. And in particular, here in yellow, you can see the intersection between the bi-star and the line inference sky maps. Well, interesting also the method in MockPy named contains, and in a multi-messenger application, you can use it to test if an EM transient is located inside a gravitational wave sky localization in a particular credible region, or it's still contained in that confidence level when a more accuracy sky map is issued. Also, Aladdin Light, of course, is able to support the mock regions. Here we can see an application in the context of LIGO and Virgo resources, in which we can interactively visualize the sky localization with the Virgo and without Virgo of the GW event 17817. The error box is provided by Fermi for the gamma burst 170817. And finally, the location of the macronova detected by SWOP telescope in Chile and the host galaxy NGC 4993. We can do the same in the Aladdin desktop. I just took a few screenshots from the LIGO and Virgo user guide in which we describe how we can build the credible region, and after that, how we can query VZF from mock. The tutorial is hosted at the link copied in the slide here. Well, the space and time mock will be described in details from Pierre's talk in the next time slot. And shortly, the method is based on a discretization of space and time dimension. The time coverage for the last order is 1 microsecond. And this system is very interesting for deep investigation in the multi-messenger application, but not. So we can encode the GW credible regions with the trigger time for doing space and time operations simultaneously. The user interface of Aladdin is very friendly. You just need to copy the trigger time from the header and paste it in the property windows, like in this screenshot. And let me show you a very basic exercise. Here we can see a random EM follow-up of an GW event. And I want to study any possible macronova emissions. And for that reason, I selected the 3 time intervals from micronova model and very schematic kilonov light curve. And by using the STMock, I found the associated coverage in each time range as selected in my model using intersection union in a loop. And so here are the final results. It's a very preliminary exercise with no real data, but an additional exercise is provided by Alessandra with real data. In the poster, search for spatial and temporal coincidence between lat Fermi exposure maps and the GW sky localization. In details, Alessandra shows the steps to create an STMock from Fermi-Lat and LIGO and Virgo data, making operation in space and time simultaneously. Okay, so by looking for the future, ET will be, sorry?
Giuseppe, two minutes, Giuseppe.
Oh, okay. So just a few words about the Einstein telescope. Will be a ground-based interferometer and will be built a few hundred meters underground. The arm length will be increased by 10 kilometers compared to 3 kilometers for Virgo and 4 kilometers for the two LIGOs in the United States. Today, two candidate sites are under investigation, one in Sardinia near the former Sostenatos mine, and one at the three-border region of Belgium, Germany, and Netherlands. It will have a triangular shape corresponding to three nested interferometers with the more isotropic antenna patterns without the blind spots. And while this introduction, because of the expected detection rates using this kind of technology, it's very impressive. 10 to 5, 10 to 6 black hole and 10 to 4 neutron star mergers per year. The simulations are provided by Maggiore et al. So we try to explore real-time access, querying the ET scale localization, encoding, of course, in STMOC by a selected time range. In other words, if you identify an interesting transient, you can query the ET schema by time ranges. That is the idea and the approach that we are exploring in the working package 3 of AHEAD. And finally, my last slide, we use also MOOC and HIPS for educational. We try to mimic the popular app like Google Sky Map or Stellarium using dedicated photospheres, dedicated HIPS photospheres. So you can get more details in the poster from Valerio about this work. So many thanks for the attention.
Apologies, I was still muted. Okay, many thanks, Giuseppe. Apologies for that. Are there any questions for Giuseppe? Okay, then maybe we move on because I see we are just a few minutes behind. So many thanks, Giuseppe, again. So thanks a lot. So that's the end of the first, the three contributed talk. And now we're going to go to a focus demo by Mario Juric on the science platform. So I think, Mario, I'll give you the floor straight on.
Thank you, Christoph. Let me get my slides up. Okay, just to verify that you can see the slide. You can all see the slides?
Yes, perfect. Yes, okay. We can see you.
Thank you, and it's always good to be on ADASS, even if virtually, even if at 11:30 p.m. local time. I'm Mario Juric. I'm from the University of Washington Dirac Institute, and I'll tell you something about the checkpoint restore and live migration for science platforms, and I'm actually going to demonstrate what we did there as a prototype. So to quickly just introduce where I come from, I'm the director of Dirac, which is a center built to advance and support research with complex or large astronomical data sets, analysis in particular. We have a very strong software group in Dirac, more than about a dozen people, total of about 25 people in total that are working on various technologies related to astronomical software. One of the things that Matthew mentioned, the streams for ZTF and LSST and the introduction of Avro and Kafka as a transport layer were pioneered here with Maria Patterson and Eric Bellin specifically. But what I'm going to focus on today is our science platform research, and specifically the one aspect of making them a bit more efficient. So to motivate this a little bit, let me talk about the present day archive architecture. So this is typically how users interact with archives. Archives are these places where there are large data sets in the back end. The user is out here and they access through a front end some subset of that data set. They access the subset, they download it, they run analysis on a local analysis resource, repeat that over and over again until they converge to what they care about scientifically. And we all know the issue with this, and the issue is this this paradigm breaks for large data sets. ZTF is already making it more difficult. LSST will definitely make it more difficult. Even 0.1% of LSST is still an order of a terabyte. The solution's been known for a while now. It's bring the code to the data rather than bring the data back to the code, which leads us to take this archive architecture that we have today, and it's likely going to morph into something that looks more like this. So what we have now, rather than a fairly simple front end that's designed to enable downloading of the data, we have rich web front ends, both portals and rich notebook type platforms, and the analysis resources now incorporated into the archive itself. Now, this is how most science platforms today are being envisioned. There's a slightly different way to build this. Rather than actually physically build the computing resource together with the archive, what one could do is utilize the cloud-based resources and simply shift all the data sets into the cloud. In that case, you could run the science platforms on the cloud as well. And there's a number of interesting things that become possible that way. For example, science platforms from one institution could access all the data sets that are available in Science Cloud at quite high speed. So you effectively get something like Science Platform from ESA potentially being able to access LSST data set or vice versa and so on. This has some interesting possibilities and opens up a way to build a whole different ecosystem of science platforms and ways to collaborate, but it is a slightly different talk. What I want to focus on here is that for all of these concepts, Jupyter is almost always the default science platform user interface. And the reason for this is that our users, the astronomers, are very used to this, this tool set, and that it's natively built to work over the web. So the bit that I said about our users being very used to this tool set is important here, because they developed a lot of expectations from years of use of Jupyter on their laptops and on their servers in their home institutions, on their desktops. They've developed some expectations on how that is supposed to look like and how one is supposed to interact with Jupyter. So what do Jupyter users expect? And this comes from 3 years of running Jupyter instances for hundreds of users, whether it's schools, educational, or whether it's locally for research. What they expect is, first of all, that their notebooks are long-lived. They expect to go to lunch and take a weekend off without closing their notebooks and interrupting their work. They also expect to have access to all their files and scripts from their notebooks because they typically run them on their laptops or on their desktops. They expect to be able to utilize almost all available memory. If they run over, what they expect to happen is that failure is soft. So that typically, what typically happens in our institution is you exhaust all the available RAM, you suddenly see a slowdown because the computer starts swapping, or you get a Python level out of memory exception. The whole system doesn't crash. That's the important message here. They expect to be able to utilize as much CPU as they can get, and they prefer not to compete for CPU and memory with other users. That's why still all of our researchers really like to have their own laptops and work on their laptops. Now, in the science platforms as we currently have them, what are users typically given? The typical implementations that everybody runs, and including ourselves for ZTF research, is Jupyter Hub and Kubernetes. There are two ways to split apart users and to launch Jupyter Hub instances. One is you could oversubscribe a large machine and therefore conserve resources, but then each user has a very small slice of CPU or memory in that large machine. Or you could go in the other direction, allocate one host per user, one virtual machine per user. And that's really nice from the point of view user. It gives them isolation, predictability, but it also gives increased cost to the operator. There are issues with how Jupyter Hub runs in Kubernetes. By default, it'll terminate if inactive for a preset period of time, by default about an hour. And that's unpleasant for a user who's used to working on their laptops and for the notebooks to run all the time. The other issue is that in case of, if the user runs out of memory, the result is hard termination. So the entire Jupyter kernel just dies. And that is because Kubernetes tries to defend against the case where one container goes over its limits. And then another issue is that if the resources are insufficient, the user must manually move to a new VM. Let's say you've assigned a 4 GB or 32 GB RAM VM. The user is doing some data analysis and realizes, oh, I need 128. Now they need to shut it down, start it on a different VM, and then rerun their notebook at that point. So the platform operator's choice here is generally either poor resource utilization or poor user experience for the user. And our experience has been the users essentially will not use a platform with poor user experience unless it's the only way to do the work. So they will fight tooth and nail not to do it as long as there's a different option. So I think there's a good reason to look into this. How do users actually use Jupyter? So everybody wants their notebooks to run 24/7. But we've actually done a study and looked at utilization patterns. And most of the time, notebooks are idle. Average research work utilization is only 10 to 20%, depending on the user and depending on exactly the type of event or work. So that's about 3 to 7 hours per day. And that kind of makes sense. And it's minimal over the weekends. Very few people actively run a lot of things over the weekends. So there's lots of room for resource management. What we need to do here is to provide an illusion to the user of a constantly running notebook. We need the ability to checkpoint it to disk while it's not being used and restore it back to the same state when the user is back. And that is something that we realized that we probably can do and went on to implement a prototype that I'm going to demo now. So this prototype is known, is called ELSA. It freezes Jupyter servers and then freezes them back again. Those of you who have daughters that are of young age might probably know where the reference is coming from. And let me show you how it actually works in practice. So here, this is in the browser. I have a live instance of ELSA running. And it's just a plain old, looks like plain old Jupyter Hub. I'm going to sign in with my GitHub ID. And the first thing that I'm offered is, which server do you want? And here we just configured 3 servers to make things simple. A small one with 1 gig of RAM, there's a medium with 2 gigs, and large with 4. Let me begin on the standard one. So what happens now is I'm going to get my Jupyter started. Nothing out of the ordinary right now. I have to wait a little bit. This is pulling the container with the whole notebook. And here we go. So the next thing I'm going to do, I'll start this notebook that we prepared for the Checkpoint Your Store demo. So what I want to show here is that I can freeze this notebook and unfreeze it as if nothing happened. So I'm going to do 2 things. This is intentionally a very simple notebook. I'll create a variable that contains the world's hello world. And then to show something a little bit more complex is I have a file here that's called test file that has this contents. These are individual lines. This is a test file. It shows that open files are checkpointed correctly. And what I'm going to do is I'm going to open this file in Python, and I'm going to read a couple of lines. So here's this is a test, and I'll pause here. So now what I'm going to do is I'll hit this button here. Oops, I actually have to save it. I'll hit this button. And what that's going to do is it's going to take the contents of the memory and everything that's changed in my Jupyter server and store it to disk and shut down my Jupyter server. And that usually takes about 20 minutes or so. And we actually know how to speed it up significantly, just haven't gotten to it yet. And here we go. At this point, my server is down. I kind of stopped it halfway through that notebook. What I'm going to do next is I'll start it back up. So this looks the same like before. I'm going to pick standard again, and I'm going to run start. But now what's going to happen is rather than that this server being started from scratch, see this message? It's going to be restored. And if you look at this notebook, note that it's green. It means it's running. So if I go here, and now I can go and print the value of this variable. Note that this is input 8, and it's still hello world. And let me read a few more lines from the file. Here we go. We stop the test and continue that file, just as you would expect. Let me try it again. Now it's white space, and then it shows, etc., etc. So what I showed you just here is that we've developed the ability to take a running notebook, store its state to disk, and then restore it on the same machine. This is already great because it makes it possible for users to, or operators to store inactive users' notebooks on disk and then restore them when the users are back without loss of work in those notebooks. But we can do better than that. This button here is a shorthand for migrate. What I can do is I can take this notebook and then checkpoint it, and rather than restoring it on the same machine, I can send it to a larger machine. So note here, this tells me that I have 800 megabytes of RAM available in this VM. Now I'm going to send this notebook to my medium server. So again, this goes to checkpoint process. It takes about 20 seconds or so. And then after checkpoint is done, because I hit migrate, it's going to immediately start this server on, start this notebook on a different server. And here we go, now it's running, now it's starting it up on a different server. And when it comes back, okay, let me go to my notebook. One thing to note this is now 1.8 gigs that they're running here. My hello world is still there. I stopped at shows. Let me read a few more. That open files are checkpointed correctly. I could continue this demo a bit more. I can now move this, this notebook back to the smaller machine because I'm still using less RAM than that machine has. And you can now start imagining all kinds of resource management things you can do with this capability. That all works. So I'm not going to do that in the interest of time. I'm just going to stop it. Now, let me go. Oh, here we are. One thing you may ask is, well, you basically didn't run anything here. Will this really work with a more complex piece of software? And to show you that it will, what we did was we loaded up all of LSST's 2 or 3 million lines of code of the LSST stack into this system. And here's a notebook that depends on LSST code. This is actually a demo of the LSST deblender. And so what I can do is, let me start this. So this bit here imports all of the LSST AFW and image and detection. And these are quite sizable pieces of code with both C++ and Python, C, external libraries, etc. And so what I'm going to do here is this element here actually reads a data repository, an LSST data repository, which is an internal database. So this opens a SQLite database to find out where the files are in the system. And I'm going to run this kind of halfway through. This may take about a minute or so. Let me get to this point. So it will take about 30 seconds for it to get, 30 seconds to a minute to get this point. What's happening right now is this code is loading a number of images, and you can tell that the memory is getting uncomfortably, memory limit is getting uncomfortably high. It's loading a number of images, and it's going to, once it gets to this point, it's going to show us RGB coads of the images it loaded from this data set, from this repository. And so I think this is going to take a matter of 30 seconds or so. Here we go. And here's a nice image. This is a fairly complex piece of code. This is 10 years of development is in this code. And what I'm going to do now is I'll checkpoint this. I'll basically migrate this notebook to my large instance. So I'll hit migrate and go to large. Now, one thing you're going to notice here is that this migration will take longer. It'll take about a minute. It'll take probably a little bit more than a minute. And the reason for this is quite amusing, let's say. The actual checkpointing of this process takes something like 4 seconds. The rest of the time is spent in gzipping the output files, because by default, the software we're using for checkpointing, and I'll talk about it in just a second, wants to really gzip all the checkpoint files, and there's no way to turn that off. This is a very trivial fix that we're going to make and submit upstream to be able to avoid zipping. And that will, in essence, turn this from a 1-minute operation to something that's closer to a couple of seconds. And here we go. And so now it's restoring on a larger machine. And it's almost there. The restore, as you can imagine, also takes slightly longer because now it has to unzip this this file, and this is all running on a fairly small server for this demo. But here we are. I'm going to go to my notebook. Let's see, where did I leave off? Here. I'll just run this cell. This is now building another RGB code, and here it is. So this shows that, and note that the available memory has changed. So this shows that I can actually move a quite complex piece of code from one machine to another. So I'll stop with my demo here and go back to the slides. What is it that our present system can do? It's multi-user, it's fully scalable, so it'll grab new machines as needed as there are more users. Jupyter Hub deployment. Each user is allocated their own VM. VMs have swap, which allows them to degrade rather than fail when memory is exhausted. And you get out of memory conditions at a Python level. As a Python level failure, you don't get the whole kernel crashing if you run out of memory, which is what you often see in Kubernetes deployments. User notebooks can be checkpointed and VMs deallocated, shut down. So that means there's no spend, no money being spent while they're checkpointed. And when users restore them, it reestablishes all state. And there's a little bit of asterisk to that, and I'll tell you about it in the next slide. This gives the user the appearance of an always running host. It's quite useful. VMs can be migrated to different VM instance type, or I should say Jupyter notebooks can be migrated to different VM instance type. And you can go both ways. You can upscale and downscale. The software sees new CPU and RAM without restart. That is really cool. You can start some analysis, realize you don't have enough memory, move over to a larger memory host, finish it without having to restart your notebook. Sometimes you build notebooks that take half a day to get to the point where you are at, and you really don't want to restart them, and this enables you to do it. And checkpoint restart times are sort of reasonable, but they grow proportionally with RAM size, and we know how to fix this. This is one of the first things we want to fix in the next couple of weeks. Limitations. Right now, there's no preservation of open TCP connections. So if you have a TCP connection that's open to the outside, that will get broken. Now, the good thing is we actually know how to fix this. The software that we're using underneath has the ability to migrate TCP connections as well, and that's one of the first things to do. We cannot checkpoint some unusual APIs in corner cases, which typically don't appear in scientific software. Just for laughs, we tried to dump a full-blown desktop VNC session that we were running within Jupyter, and that didn't work because it was complaining about iNotify. HPC libraries with special hardware support and InfiniBand libraries and so forth may not, it's not clear how they're going to work. Again, it's not clear that we need them in this context. And the thing that we do definitely need is support for GPUs and accelerators. Right now, there's none. So if you're using a GPU, you cannot checkpoint. But this is something that's being worked on. The important bit here is that failure to checkpoint is non-destructive. If the system isn't able to checkpoint a notebook, it can just give you a message and say, I cannot checkpoint, please continue working on it as is. So you're not risking your work by trying to checkpoint. And that's a really nice feature. All All right, given this is ADASS, this is the fun part. Let's talk about technology. Let's see what's under the hood and how this works. This is the high-level architecture what we have right now. So the deployment that I just showed you runs on DigitalOcean, which is a cloud provider that's just really convenient for development. We chose it for simplicity. We can run this. We can move this to AWS, GCP, or Azure relatively easily. It's standard Jupyter Hub notebook containers and both for the hub and the notebook. And a fairly standard setup. They're running directly on VMs, and we've written our own lightweight orchestration layer. The reason why we couldn't use Kubernetes is because it has no support for checkpointing and no swap. But in the long run, we'd really like to integrate this with Kubernetes. We use Podman as the runtime engine, as the container engine rather than Docker. I'll tell you about that in a second. And for checkpointing, we use something called CRU, which is the most interesting bit, I think the most important bit in this story. What CRU stands for is Checkpoint Restoring User Space. It can freeze a running container or individual application and checkpoint a disk. It started in 2011 by OpenVZ developers, and it was merged into the mainline kernel in 2013, late 2013. So it's been there for a while. And the main insight that they had was that the Linux kernel already supports numerous interfaces, freezing, inspecting, and changing the state of a process. So that means that you can probably dump it from user space. And that's what they did. There was a lot of skepticism early on. This is a famous / infamous post by Andrew Morton, one of the kernel developers, that this is a project by mad Russians to perform checkpoint restore, et cetera, which is why I love this thing, because it's kind of a triumph of the mad Russian here. It actually worked in the end. It supports checkpointing of virtually everything that we need to checkpoint containers. And the performance is such, other than the gzip issue that I mentioned, that snapshotting and restore can happen in 1 to 2 seconds. And this is really disk read and disk write bound. I don't know what the actual limit is. And there's a mode called lazy migration mode where you can actually migrate in tens of milliseconds. We haven't actually tried it out. The file system has not changed between invocations. That's one limitation. And the file system must be the same at the inode level. And this is where containers come in, because containers allow you to keep that integrity. For you is difficult.
Mario, maybe a few minutes left. So
Yep.
I don't know if you want to take questions. I mean, there is at least one.
I have maybe 2 more minutes and then I'll take questions. Okay. So the bit that's really important that made it this easy to use is Podman, which is Red Hat's implementation of Docker. Basically, with these 2 commands, you can now checkpoint the container and restore it. And then the thing that we spend most of our time on is integration with Jupyter Hub. Now, I'm going to skip most of this in the interest of time, but there are a couple of levels. We had to implement orchestration that works without Kubernetes, because we cannot use Kubernetes because it doesn't support it yet. We've implemented it using Jupyter Hub spawners, and it's a quite elegant implementation, only about 400 lines of code. The user data storage has to be on a shared file system, so on a network file system. That solves the problem of how do all these different machines see the same file system when you actually move processes from one to the other. The backend integration is such that we've overridden the start and stop points in Jupyter to mean checkpoint and restore, or restore and checkpoint. This is not ideal, and we should really modify Jupyter upstream to have true checkpoint and restore, but it works for now. And finally, we built a user interface that you've seen. So why is this useful? Because now, if you're running a shared server, you can opportunistically checkpoint inactive processes. And let's use a snapshot from our group server, and there are many of them and take up a lot of memory. If you're running on-premise SaaS platforms, you can give significantly better user interface because you don't have to terminate users. You can just checkpoint them. But if you're running in the cloud, this is where this becomes extremely useful. So we've looked at how what the duty cycle of a typical notebook is. It's about 15%. And this, combined with running on spot instances, which you can now do, can bring your cost down by more than factors of 10. So here's an example with an M5 instance. And if you think that you can work with a T3 instance, it gets even better. So we're talking about potential factors of 10 here. So this becomes comparable and sometimes better to than on-prem total cost of ownership. So to finish this, looking ahead, these are the things that are going to land in the next couple of weeks to months. Speed up, speed up, speed ups. That's the most important bit. We'll do some generalization, migration of network connections. Sub-second line migration is on the horizon, and Kubernetes integration is one thing that we would really like to do. And there's a ticket that started that. If you want to test drive this, let us know. Go to this repository and open an issue. And we're really looking forward to collaborations. We at Dirac, we develop software. We don't tend to run it other than for ourselves. And we'd love some collaborations here with platform operators and software enthusiasts to go and build this further. So thank you, and love to take any questions if there's any. And if you like work like this, join us. Here's a link to a couple of job ads we have out. Thank you.
Thanks a lot, Mario. So I think there is one question from James Tocknell. How are ABI issues handled?
ABI issues? Can you be more specific?
Okay, then
I don't see ABI issues here.
Okay, well, I don't know. I can't. Or maybe let's do the following. Can I suggest, if James is online, that maybe he can ask the question directly to Mario through Discord. Then you can be more specific. So because it's it's okay. It's time to move to the buff. So okay. So thanks a lot, Mario. And thanks. And then I think we move now to the buff about the standardization of data formats in gamma ray astronomy, which will be led by Cosimo. Cosimo, are you online?
Yes, I am. Can you hear me?
Yes, perfect. We don't see you yet, but
can you see me now?
Now we can see you.
Right.
Yeah. Very good. Okay, so I think I leave you the floor now for the full session.
Okay, thank you very much. I think Cosimo,
just one thing. You
yes.
might then have noticed that you are now co-host in Zoom, and so that means together with your co-organizer, that means that you can promote any attendee you want to be a panelist so that they can share their screen and give presentation. If you want to do that, you can.
Okay, I see. Okay, thank you very much. I think Peter contacted me. He said that he will share the session. So in case there is something that he wants to say, please.
Oh, I have nothing to say.
Okay, perfect. So I can start. We will present you today the effort of defining a standardized high-level data format for gamma ray instrument. And we will first present the format itself and then the projects that have successfully employed it. And to me, there will be Tarek. Tarek, are you online?
Yes, I'm here.
Okay.
Can you hear me well?
Yes, show yourself, please.
Okay, I was searching the Zoom window in my madness. And now I have the video on, just so everybody can enjoy my face.
It's black. We cannot enjoy it, but okay, now we can see you. Okay. So yes, Tarek will help me with a session. If you have question and you are not in the Zoom, please do post them in the channel in Discord. And we would like to start asking you a few questions. Please raise the hand if you have expertise at all in gamma ray astronomy. So please attendee, raise the hand if you have a basic knowledge of gamma ray astronomy. Okay, Bruno, Gernot, and Matthias. Okay, now raise the hand if you have an experience with data standardization in general with the astronomical instrument. Okay, only 1, 2. And last one, if you have experience with data standardization for gamma ray astronomy.
Okay, so very few people. In general, it was 1 or 2 or 3 positively replying to the question. So I will start to share my screen. Can you see my screen? Can you see the screen?
Yes, Cosimo, perfectly.
Okay, so as I said, I will start introducing the format itself. So this data format for gamma ray astronomy instrument. So I always like to start this topic with this fresco. It's a painting by Raphael, and it's called The School of Athens, and it represents Plato and Aristotle having a discussion about the nature of things. And I'd like to imagine they're having a discussion about gamma ray astronomy. So Plato, believing in the heavenly nature of things, is pointing to the sky and suggesting to detect gamma rays with an orbiting satellite. And Aristotle, believing in the earthly nature of things, is pointing to the ground and suggests to detect the Cherenkov light from an electromagnetic cascade started by a gamma ray that hits the atmosphere. But despite the different philosophies, the two philosophers can actually speak the same language. And today in gamma ray astronomy, we are somehow in the reversed situation in which we have the same philosophy, the same objective, but different languages. So it's more similar to the situation of the Tower of Babel, let's say. As a matter of fact, neither data format nor data model is shared by current gamma ray instruments, and multi-instrument analysis basically require custom expansion of proprietary software. This also means that if we want to release our current data, if we want to make a public legacy data release, then we would need to release our internal analysis tools that are not designed to be used by a large community. So let's see in general how the different gamma ray instruments deal with data standardization and data sharing. So Fermilat is the major instrument for gamma ray astronomy from hundreds of MeV to hundreds of GeV and beyond. And all data, in this case, in FITS format, are publicly available and promptly disseminated. And there is a web interface that allows any user to retrieve them. The open source, the science tools are open source and they are publicly available. And they also have a very nice Python wrapper that allow you to perform an entire analysis within a Jupyter notebook, let's say. The situation is very different for imaging atmospheric Cherenkov telescopes. Until the last decade, let's say, all our Cherenkov telescopes were operated as experiment. This means that they had order of hundreds of members, and the data access was private. In the same way, the analysis software. Also, the data format was custom. So each telescope has its own data format and software. And it's mostly based on root and C++ and root. This is because people involved in very high energy gamma ray astronomy are usually coming from particle physics. So they inherited this setup of using C++ and root. But the next generation of Cherenkov gamma ray telescopes, the Cherenkov telescope array that is already in construction, will be operated as an observatory. It will have a much large number of members, thousands, and both its data and its science tools will be open to the astronomical community. And we will move to a FITS data format, at least the one that is proposed now, and to the tools that are currently in development and are candidates for to be science tools of CTA are written in Python, or they're written in C++ with a Python wrapper. So I want to stress that the operation of the next generation of Cherenkov telescope array poses this requirement. So on public analysis tools that you can check the GammaPy poster by A3, but also on standardized high-level data format. And this will be the topic of this talk. So members of the ESCT community channeled the discussion about this standardization in a forum. So there was an initiative to define this format that started in late 2015, and they come up with this solution. They created a forum that is basically a Sphinx documentation that is built via read the docs and that is contained in a GitHub repository, as you can see here. The docs contain the specification for the content, the naming scheme of the data. So the suggested support is FIT files, and within the documentation you find the kind of data units, header, the column that you have to include in your file. And any change in the format is discussed via issues and implemented via pull requests. So anyone can get this chance to contribute to the format, provided that the community approves and supports his or her changes. So which data level do we choose to unify? A telescope of the current generation of Cherenkov telescopes produces an output that very roughly is of the order of terabyte per telescope per night. So very ballpark number. And this is the raw output of the DAX, so whatever event the data acquisition is recording. We choose to include, to reduce our data and to store what we call the data level 3 that consists of gamma ray candidates and response function of the system. Now, for the other astronomers that are not familiar with the gamma ray astronomy, we detect, for example, Cherenkov telescopes detect also shower from cosmic rays. And also gamma ray instrument orbiting are affected by cosmic rays. So we have gamma ray candidates are events that have triggered the data acquisition, and that we can safely identify with a certain confidence as being generated by gamma rays. And the response function, I think any of you is familiar with that. It's just the response of the system that we can factorize in 2 or 3 components. So this is what actually we store in the DL3 FITS files. So we have a data unit for the events. You can see it here. We have the ID of the event in the data acquisition, the timestamp of the event, the right ascension and declination, so the coordinate of each gamma ray in the sky, and its estimated energy. And then on the right, you can see the header data unit containing one of the IRF component, the effective area in this case. And in this case, it's just an array. You can see it here. Effective area binned in so an array of values given certain bins of energy and theta, which is the offset from the detector center. So as I said, the initiative for this standardized data format is for the next Cherenkov telescope array, but actual current Cherenkov telescopes already can embed, accommodate their data in this format. And also open source sign tools, as I told you, GammaPy and CTools are in development as prototype for the CTA analysis software. They can already read it as input, so they can perfectly operate with this data. So a bit of news about the current development in different experiments. So for what concerns spaceborne instrument, they have their own standardized. So Fermilab has its own standardized data format, but this data with few modifications can be made compatible with this DL3 data. And we will see it later, a project that actually does it. Then the current Cherenkov telescopes, all of them have an active DL3 group. HESS telescope was the first to actually make a public data release in this format, which will be the next topic in this talk. And then FACT, Veritas, and MAGIC released just a small sample of the Crab Nebula in this DL3 format for a specific project. And then the large size telescope, which is the first element of the future Cherenkov telescope array, has already started to test to reduce some of its high-level data in DL3 format. Also, water Cherenkov telescopes with few modifications in their data can embed their data in this format. And I'm aware that there is a current effort in HAWK to produce a small test DL3 sample. So I will give you a bit of notions about what kind of analysis we can perform with this DL3 data, because later I will be talking a lot about binned and binned likelihood. So I wanted to give you an idea of what it is. The objective that we have when we analyze the data is to estimate the flux as a function of energy of one or many sources in the field of view. So for what concerns the data reduction, we can do either 1D analysis or a 3D analysis. In the 1D analysis, you will estimate the spectrum of a single source in the field of view, and you will extract signal and background counts from the event list itself. So given the events that you have, you can see them here. You can see here the right ascension and declination of all the photons in an event list. You see that the cluster of photons of gamma rays corresponds to the source. So you will use this as a signal on region, and you will extract the background from another region not containing the source. So in this case, we integrate the spatial information in this way. we reduce the spatial information in this way. Or you can do a 3D analysis. So you will bin your data in rate ascension, declination, and energy. You can see this image of a cube of an event list. But in this case, to perform the following analysis, then you would also need a background model of your instrument, because in this case, you will not be able to estimate the background directly from your data. And for the parameters estimation, we usually we either use an unbinned likelihood. So given a field of view model, given a model of all the sources, positions, morphology, and spectra in the field of view, we can compute the likelihood of each observed gamma ray. Or we do a binned likelihood. It means that we bin the data in energy and coordinates. So we create a cube, as a matter, a binned cube. And then we compute the predicted counts in each of these bins, folding the IRF with the field of view model. So, so let's go to the project that actually employed the standardized data format. Let's start with the HASS first public test data release. So HASS was actually the first instrument to make a public data release of among the ACT and to make it in DL3 format. A small dataset, 50 hours of early observation were released with the purpose of software and analysis method testing. So not for scientific analysis, but to test the science tools, let's say, to offer an opportunity to test the science tools with current TSCT data, and also to support this effort for the definition of standardized high-level data formats. The release contains subsets of data that were already used in major publication, and each dataset represents a different science case. So we have the Crab Nebula, that is a point-like steady source of gamma ray. It's the brightest steady emitters of gamma ray in the sky. Then we have Blazar PKS 2155 that made an historical flare. So it's a point-like variable source with variable in time. Its flux is variable in time. Then we have a moderately extended source, steady with a constant flux. Then we have another supernova remnant with a large extension, a steady source. And then we have off data that you can use to build the background model that I showed you in the previous slides if you want to perform a 3D analysis. So you have seen already the type of data. So it's just event list and IRF stored in the data units. And this is what you can obtain with few lines of Python using AstroPy or one of the tools, GammaPy, for example. You can examine from the event list the spatial and spectral distribution of gamma rays from the Crab Nebula on the left, and from this extended supernova remnant on the right. You can see in the 2D plot, you can see all the gamma rays in the field of view. And on the right, you can see the counts as a function of energy extracted from this on and off region that I showed you before. And then the other element of the DS3 data are the IRF, and this is the effective area. This is an image of the array that is basically stored in the IRF component. So here on the left, on the bottom plot on the left, you can see the effective area as a function of energy at different offset. And on the extreme right, you can see the same plot, but made in two-dimensional. Okay, I think we can take a few questions because this project, this part of the talk concerns the data format in general. Then we will see how the data format was used to test the science tools. So I think I can stop for a second and take some questions if there are. So questions about the data format in general. Are there any? I stop for a second the screen share. Are there any questions on the data format in general? Doesn't seem to be the case, so I will continue. So, okay, let's check the project that have actually used the data in this format. So the first was, one of the first was the analysis of the HASS public data release of the specific data release with CTools, which is, I remember, used one of the candidates for to be the software of CTA, the analysis tool of CTA. It's published in astronomy and astrophysics, as you can see. So this HES test data release was analyzed with CTools. It is the first test of these tools with actual EACT data because so far the tools were tested with CTA simulation. A background model is built from the off data in the release, and then they used in a 3D unbinned likelihood on all the sources in the release. The consistency of the results is checked by doing a check against classical 1D binned likelihood methods, because the standard method that we use with current generation of Cherenkov telescopes is the 1D binned likelihood analysis. So, and this is also implemented in the science tools. So it was checked against this classical method and also against results from the literature using larger dataset from the same sources. And also there is a showcase of the multi-instrument capabilities of CTools, because CTools relies on another library that is able to read different gamma ray data formats. So these are the results of a CTools 3D unbinned analysis on all the sources in the dataset using the background model built from the off. So you can see in each of the plot the spectral energy distribution. As I said, we want to measure the flux of the source as a function of energy. You can see in red the results that was obtained with CTools, sorry, using the DL3 data. And in blue, in all the plots, you can see results from the literature using the custom software of the experiment and using a large data set. And despite the comparison is not exact, because in the literature results, they used much more data. As you can see, there is a very general good agreement between the results of the analysis software that use the standardized data format and the classical analysis software of the instrument for all sources. So as I said, more test features of CTools are tested with this data. In particular, they explore the possibility of fitting the extension of the Crab Nebula, which, as I said, is a point source for current Cherenkov telescope instrument, using this DL3 data. And then, as I said, CTools are built on GammaLib, which is a library that is able to interface with different types of gamma ray astronomical data. So here you can see the result of a spectrum in red, computed using Fermilab data without converting them to the DL3 data format, original Fermilab data, with EACT DL3 data within the same framework. So with the same framework, you can combine different types of data and obtain these general results that is, as you can see, agrees very well with the other results from the literature. Another project that used this specific data release was this, and validation of open source science tools and background model construction in gamma ray astronomy. The scope of this project was slightly larger because this project tested both the candidate science tools for CTA, Gamma Pi, and CTools using this data release. The objective was to validate the tools against each other and also to validate a new background model template that is not relevant for this discussion. So the CTools and Gamma Pi were tested against each other, and this time they were checked not against literature, but against the results of the HES proprietary software. So against the classical software, that classical custom software that produce 1D spectral analysis. A new procedure, as I said, for the template background modeling is introduced, like in the previous paper, but this time they use a lot of more proprietary data to build the background, but still. This is used to test CTools and Gamma Pi 3D likelihood analysis. So this is some example of the validation against classical analysis methods. So you can see here a significant map computed with Gamma Pi in the background, and the HES private software with the colored contours. And as you can see, there is a very good agreement between the two. So again, what is produced with the open source science tools relies on this standardized data format, and what is produced with a custom relies on the traditional root data. On the right here, you can see the results of a 1D binned analysis. So this is a classical analysis fitting a spectrum, a power law spectrum, to the different sources. You can see here the expression that we are fitting is just a power law of the energy with a normalization prefactor. And here you can see the result for the normalization in the right top plot, obtained in red with the HES custom proprietary software, and in green and blue with Gamma Pi. And in all cases, the open source software using the DL3 data gets very good results. The deviation is always below 10%. Same for the spectral index of the power law. So as you can see, the classical methods implemented in these new tools are very efficient, and also the information that we are putting in our DL3 standardized data actually reflects what is actually contained in the original proprietary data. And this is very similar to the plot that I've shown you before, but this time using the 3D likelihood of both tools. So in gray, this is always the spectrum of the 4 sources included in the data release. And in gray, you can see the results from the literature. And then in red, you can see the result of a 1D analysis computed with performed with a private software. And in blue and green, a 3D analysis computed with performed with the open source analysis tools on the DL3 data. And as you can see, in all cases, there is a very general good agreement. The last project that I want to show you has still a bit larger scope, and it is to perform data combination fundamentally, and to show also how we can produce reproducible gamma ray analysis in gamma ray astronomy. So combining data from Fermi and 4 of the currently operating Cherenkov telescope in this preliminary DL3 format, we produced a joint fit of the Crab Nebula spectrum. We produced the first fully reproducible multi-instrument gamma ray analysis, relying only on open source software. All the material, data analysis script, and notebook are available online in this GitHub repository. And the purpose of the project is to show the ease of multi-instrument analysis once the data standardization has been achieved. So on the left, you can see the instruments that contributed to this project. We took 7 years of Fermi-Lat data. As I said, they are freely available, and we performed just some small modification to make them compliant with the DL3 data format. And then each of the telescopes released a small sample of data in this standardized data format: 40 minutes from MAGIC, 40 minutes from Veritas, 10 hours from FACT, and 3 hours from HESS. And on the right-hand side, you can see the counts, the gamma rays coming from the source, obtained subtracting the background with the 1D analysis method I showed you at the beginning for each of the instruments. And you can see that we have a coverage of almost 3 orders of magnitude in energy with using all the instrument. As I said, Fermi-Lat data are freely available, and we computed the IRF with the proprietary science tools, and then we make them DL3 compliant using GammaPi. And then we used a small sample of DL3 data that was specifically released for this project. So this constitutes also the first joint release of data by current Cherenkov telescopes. These are our results. So we did the spectral analysis. We extracted the spectrum of the Crab Nebula using a 1D binary analysis, and we fitted this function that you can see here. It's a power law with an index that changes with the energy. On the top panel, you can see the likelihood contours of the different parameters of the log parabola, the plotted against each other, the different combination of parameters. And you can see the power of the data combination in the reduction of the contours that correspond to the joint fit, which is indicated in red. So the different colors indicate the classical likelihood analysis performed on the single instruments, and the red one indicates the likelihood performed using the dataset altogether, okay? And here is the result plotted as a spectrum, let's say. So the parameters combined in the spectrum. Again, you have the same color code as before for the results coming from the individual dataset of the instrument, and in red, the result coming from the global fit using all the data at once. We plotted also a reference spectrum, spectrum obtained with a theoretical model fitted to the Crab data, just to show that we are in the, there is a good agreement with the result that we produce. This is the first spectrum of the Crab Nebula obtained combining Fermi-Lat and 4 of the currently operating Cherenkov telescopes. But having the data in the same format offers also us the possibility to study the systematic uncertainties that affect our instruments. In particular, we try to cook up a recipe to estimate the systematic uncertainties in the energy scale, which we estimate is the effect that most that dominates our data, such a small amount of data. So we introduced a constant energy bias per each instrument, and we modified the assumed spectrum to account for it. So the spectrum will have a different Z for each of the instruments that are contributing to the fit. The global likelihood function is constrained with a normal distribution of this Z, where the mean is 0 and the standard deviation is the systematic uncertainty that is claimed by each instrument. You can see here the same likelihood contours as before, using all the instruments together, and but this time including this systematic uncertainty. And this is the different Z factors for each of the instruments. And Fermilat claims an energy scale of 5%. So what we obtain with our fit is consistent with that. And in the same way for the Cherenkov telescopes, they usually claim a energy scale of 15%, and what we obtain is consistent with that from our fit. So as I told you, this was the first fully reproducible, we believe it was the first fully reproducible gamma ray analysis. How was this achieved? So for the short-term reproducibility, we released all the code and the scripts in GitHub. The data, as I showed you before in the screens, in one of the previous slides, are very small. Typically, it's hundreds of kilobytes per dataset, per DL3 observation, let's say 20 minutes of observation. So the global dataset, which is few hours per combining all the instruments together, is of the order of megabyte and can be shipped with the code. Then we have simple commands to reproduce all the results, all the tables and the figures in the paper, and notebook tutorials also. All the packages are managed via Conda environment. So you can just download the Conda environment corresponding to all the tools used in the analysis and reperform it. For the medium-term preservation, in case the Conda virtual environment is not enough to guarantee reproducibility, we have also a joint grab Docker container, and we have also stored our results online in Zenodo. So this was the last project that I wanted to present to you, and I want to draw some conclusion. I think that the effort to define a standardized format for high-level gamma ray astronomical data is now fully recognized. Why? Because we had the first public release of VSCT data, of the current generation of VSCT data in this format by HES and then jointly by the other ESCT. And also because having a standardized data format offered us the possibility to thoroughly test the science tools in development for the next generation of Cherenkov telescope arrays. And we see that the information that we embed in this data, that we reduce in the standardized data, actually allow us to perfectly reproduce the results that we have obtained so far with our own private software. Thanks to the data standardization, we can already produce gamma ray analyses that are multi-instrument, reproducible, and that rely on open source software. So I like to show this scheme because I think it summarizes the main points of our work. So once we have defined a common data format, then multi-instrument science is already possible because you just have to adapt the data of your instrument to this format. Then if there is an open source science tool that is actually compatible with this data format, that is able to read data in this format, then reproducible results are achieved without any effort. And this will be a key asset for the current and future instruments that plan to extend their data access to a wide astronomical community. And that was all for my presentation. And I think we can open the floor to discussion now. There is a question from Bruno.
Yeah, do you hear me?
Yes.
Yeah, thank you very much. So thank you a lot for this nice explanation of the goals of this common format. I just wanted to add one point, is that so you are focusing on this event-wise data format that is, as you have well explained, the basis of multi-wavelengths, but also multi-messenger science analysis, because indeed detector like IceCube or Chem3Net could handle this kind of format to make joint analysis also. But just my comment was about about the output format of these science tools, which is out of the scope of your presentation. But I wanted just to say that also having a common format shared by the community at the level of DL5, so products like curve, maps, spectra, but in DL6 level also like catalog, will allow the community also to make to share results, to make a multi-instrument analysis, and this was also mentioned yesterday in a talk when people were using catalogs, and they mentioned that the difficulties they have to handle the data. What are the data? How and the understanding of the data, it takes a lot of time on manpower. So it was just a remark that maybe in the future we will need to also standardize the DL5 or 6 format for the community. But let's focus on the DL3 first.
Yes, thank you. Indeed, it's one of the possibilities also to extend it to the multi-messenger domain because the information that can be embedded is relatively similar. There is a question in the chat by Dirk, and I saw that Bruno has already replied to it. So Dirk asked, what is the size of this data set? And yes, you can see these are all the data contained in the first SDL3 data release. And as you can see, it's order of thousands of kilobytes per each of these run is 30 minutes observation. So then you can add them up. So I would say that the rule of thumb is 600-700 kilobytes per 30 minutes of observation, reducing the data to event list and IRF components.
Let me very briefly discuss on this, because for those external to our community, they might be surprised about why our data sets are so horribly small, and showing the plots, looking at the plots that Cosimo showed, seeing excess of 70 or 60, they might be surprised. So those are indeed photons, but in the energies that these telescopes operate, in the very high energy regime, the expected rates of gamma rays, it's extremely small. That's mainly the reason why these data sets are so small. Actually, the data describing the performance of your instrument, the instrument response functions, usually take more storage than your actual data, so the photons themselves. No, so for those of you external to our field, that is the reason why our data products are so small.
More questions? I don't know if anyone that is more experienced than us with FITS data would like to give us more feedback, because I mean, we have moved very recently to FITS data in gamma ray astronomy. So perhaps, let's say, astronomers at other wavelengths that have used them since a while can give us more feedback or their experience with it, if they're planning to move to others data support, let's say.
Jose Enrique made a comment. So in which of these data sets the model should be applied, the big or the small data sets? I'm not sure about which model Jose Enrique is referring to. Actually, let me very briefly go back to Bruno's point regarding DL4 and DL5, and then we go back to the Jose Enrique, because so this is interesting, because is there something specific to our high-level products that should be different in any way to the rest of the community? I mean, of course, our spectra are, let's say, very low statistics as compared with obviously optical spectra or even X-ray spectra. Yeah, there are like two conversations in parallel right now. So I know that that there has been some effort on standardization on also gamma ray spectra, but for example, for Fermi-Lat, Bruno, are you aware if some effort was done to actually try to converge with the rest of the community with other wavelengths? Such as spectra, light curves, etc.
Personally, I'm not aware of that, but I'm not a Fermi guy, so I cannot answer you correctly.
Yeah, this is certainly something to explore. Yeah. Yeah,
Okay, so they are making question on Discord and they are rightfully saying that a question on Zoom get deleted, but if you ask them, if you raise your hand and speak, it will be recorded. So James actually asked us what file format did Gamma Ray Astronomy use previously? So for what concerns Fermi, Fermi had already the data released in this FITS format. So both the event list and instrument response function are stored in FITS file like we do now. Basically, we took a lot of inspiration from Fermi. And instead, as I said, very high energy gamma ray astronomers were basically moved from particle physics experiment. And so they were accustomed to use root and C++. So for example, I'm a member of MAGIC, and in our experiment, we reduced the data to root files. Basically, all the data levels that I showed you in the table from data level 0 to data level 3 are embedded, stored in root files with different attributes. We basically use specifically root trees, basically. So each event has, it's an entry in the tree with all the properties like the direction, the energy, etc., etc. Does this address your question, James? Something else you want to ask? I'm asking him to unmute himself. Okay.
Dirk also raised his hand.
Yes.
So,
well,
please,
since nobody else is asking questions,
please.
I can ask something minor. So what fit standard are you using? Are you up to date there?
Yes, I think it's the 4.0 for the one that we used for the joint grab release. Yes, so it's the latest one.
Yeah, I can only say this is a big and very nice step forward that you've made. It's fantastic. It's going to allow CTA to become a real proper observatory. Congratulations.
Thank you. In which waveband are you involved?
Well, I started in very high energy gamma ray astronomy long ago in the 90s. You might have seen my papers on Markheim 421 and 501 and so on. But then I was actually working for Fermi later, and then for Integral, and now I'm working for ALMA.
For ALMA, okay.
And ALMA has used exactly the same type of software stack, so to speak. I mean, we are also working with an analysis software that is C++ with a Python wrapper. It's called CASA. So it's all very similar in terms of the tools. However, for our data format, we are not using FIT, but some, so to speak, proprietary format, but never mind. So the only thing we store in FITs are really the images at the end. So I assume you also have tools then that create images. I mean, the actual astronomical images.
Yes, they're the high-level science tools.
And those are also using the proper standards and so on.
Yes, exactly. This is another thing why in general, I think both 3D analysis, but also
this kind of visualization was never done in previous experiment, because now we have all these fantastic routines for astronomical libraries like AstroPy, and this was missing in the in the past. So I think this is also one of the reasons for which it was a bit more difficult in the past to do this kind of to produce maps or cubes in general. Because
So
when we do the data reduction in 1D, we do the classical 1D analysis with, I will share my screen again.
So the problem that the instrument is so strongly weather dependent, you have solved by having a per run or per, what do you call it, execution block, we call it in ALMA.
Run.
Per execution block instrument response function, correct?
Yes, it's also to account for different, not only weather condition, because, for example, there are other observational conditions that change the response function, basically, especially, for example, the zenith angle. So the zenith angle that you are pointing to will change the
I know.
the energy. So yes, exactly.
Yes,
so it is, let's say, a recipe to have a stable. We are more or less in the ballpark sure that in that 30 minutes the observation.
But I mean, the zenith angle dependence should. I mean, that's a parameterization that should not depend on the day the observation was made. That could somehow be generalized, no?
I don't know, because
can I step in, Cosimo?
Sure.
So this is a very good question. So it all depends on the systematics levels that you need, no? So for the current generation, so we essentially perform simulations on a given set of parameters, no? So in zenith and azimuth, for example, so you are observing Markarian, it's moving across the sky. You can have a closer to the simulation distribution of events to calculate your instrument response functions, etc. But for CTA, for the future observatory that will be using this format, the systematic requirements are much tighter. So we really want to go to the few percent level in systematics. So for that, doesn't matter that the zenith evolution in the sky will be the same every day, but for example, the different light illumination that you have in the sky that given night, or for example, the density profile of the atmosphere may change from one night to the next one. So the deeper you want to go into the actual systematics that you expect, it will become way more complex.
I mean, you're definitely on the safe side by having simply everything just per time slot without trying to generalize.
Yes. So, for example, Hess, I believe in the past, maybe Bruno can comment, but Hess in the past did some data releases, and actually they internally export all their data into this format, into this DL3, no? And when they do export all their data, what they do is they export their event lists on one side, and then their instrument response functions in another side. So they are not physically embedded into the same FITS files, okay? So then when they perform a gamma ray analysis, what they do is they, let's say, connect via software the specific event lists with their specific instrument response function. So you don't need to duplicate so many times the same instrument response functions for runs that will be relatively similar.
Yeah, exactly. That's what I would expect. That's kind of the way to go. Yeah. Okay. Thank you.
Bruno, please. You muted yourself.
Yeah, sorry. Thank you. Thank you. Just to continue the answer of Tarek to Dirk. One thing that is interesting in this format also is that we have in the space mission define good time of interval GTI. So this concept is very useful, I think, even for us, because as you know, the instrument response files, the instrument response of our telescope can change rapidly when we observe at low altitude. So due to the variation of the zenith angle. And then during our observing block, so which is roughly 20 minutes, 30 minutes, the response of the instrument can change significantly. So by introducing the GTI, and as proposed in this format, GTI, one interval is such that the instrument has a constant response. And so we can link in a unique manner one GTI to one IRF. So if within one observing block we have we notice that we should change the IRF change significantly, we can then able to create 2, 3, or 4 GTI within this observing block and link one GTI to one IRF. And I think this is also an improvement compared to what we have. Also, the interest of having an OB IRF, a runwise IRF, is the following: when we have major observatory like ESS or ALMA, we know that we have hardware configurations that can change, a telescope that works or doesn't work, or that we are in the building phase. And so, the response of the instrument will evolve with time. So it's quite important in order to provide a good systematic level for the astronomer of our data to associate the correct IRF to the correct run.
Thank you. Matthias also wanted to intervene. Please, Matthias.
Yes, hello. But actually, I would more switch topics. So I don't know if you want to discuss a bit further this particular point that you were just discussing, and then I chip in afterwards.
Let us give give us the opportunity to bring a couple of questions from the Discord, and then we can give you the word. Is that okay?
Yes, sure.
Okay, so
yeah, so
James
for example,
asked if there is any idea that we can take from root that we should think about other formats.
Yeah, so I briefly answered in parallel. So the thing is that those of you that have worked with root, they might automatically think, no, there is no way that we can learn anything for astronomy. But I mean, root is strongly based on the basis of very quickly going through a list of events, and each of those, let's say, entry into a root file will have a very complex structure, let's say, no? And it is actually very useful and very efficient to do exactly that. But in astronomy, as it was briefly discussed before, usually what you want is an image or maybe a spectrum in some cases. But the root format, it has been really developed thinking about particle physicists, and in general what they need is a very deep set of libraries for accurate statistical analysis of those events, and which relates to another comment that Robert gave, which is just the anecdote of him not finding a fitting routine for his specific use case, and he found it in root, which is exactly it. So root is a set of libraries in C++ that actually are extremely useful for particle physicists, although I'm really not sure how much we can learn to incorporate into other formats. I really cannot think of that many cases in which maybe in X-rays and soft gamma rays we can definitely perhaps such a data serialization is useful, but again, like I'm not really sure. I'm certainly not an expert on that.
And then Sonal asked if the data format is frozen. It is not, because as I showed you, everyone can propose a change. So when other instrument perhaps need some other metadata or column, they can ask it to be added. And indeed, Jutta commented that in KM3net, they're actually taking a look at the format and trying to implement it. So before going forward, let us let Matthias talk. Please, Matthias.
Yeah, thanks. Actually, my questions or my topics were a bit related to this last question. Yeah. So maybe just to comment also, for example, from the viewpoint of CTA at this moment. So CTA is currently undergoing several, let's say, revisions of previous definitions that we have been doing in the past years. For example, we are just now looking more closely once more on the definition of the instrument response function and how we describe it. Yeah. That would certainly lead to an evolution of the format, and what that might then be different to what is currently documented in this open gamma ray format. Yeah. Which we use as an input certainly also to define the data model, DO3 data model and upwards that we have for CTA, but we indeed also expect it to evolve. Yeah. So certainly for us it's not frozen, because in CTA we have not yet chosen the final format for the data model, so the content of DO3, but the format we expect to have it available in FITS format. Yeah. Which brings me a bit to the topics or the questions that might be a bit relevant for this session here, because you called it standardization of the DO3 format, right? And a bit what triggered me here then asking the question is, what makes a format a standard? Yeah, and okay, that question is maybe a bit philosophical sense. But on the other hand, it has a bit direct implication, because what could be nice also to discuss here in this forum is exactly these questions: how to evolve formats, especially when they have been initially driven by a community rather than by experiments. What are the stakeholders for exactly the gamma ray format? And I agree with Bruno that the whole multi-messenger and multi-wavelength community that would allow, and especially one of the drivers that you have not mentioned in your slide, interoperability, that is really important for this format, which is also for us important as CTA, because we want to position ourselves in the multi-messenger astronomy, right? So who are the stakeholders to include in the discussions, and what is actually the right forum to discuss further evolution of this format? Yeah. You certainly mentioned the Open Gamma Ray initiative, but is this the right forum, and how does it, for example, what is the role of the IVOA and the interaction with the IVOA that we might also want to look in the gamma ray community to achieve for standardization of a format? Yeah. So these might be, these are some questions that now popped up during this session also for me.
And can I answer briefly, Cosimo? So
Yeah, sure.
There are several points that you brought up, Matthias, but everything is related to right now 2 points. First, it is an evolving thing, so it is certainly not fixed. And the second one is to extend it to other event-based observatories. No, so there are like these 2 open questions that we are discussing, and also how to standardize it. No, which is the point that Matthias brought. I actually, so in our experience over these years, it simply did not happen that we were able to impose anything on anyone. Okay, so it always throughout the evolution of this data format or data model, if you want to call it, what happened always is that a given, for example, a given analysis software or a given experiment or a given use case appeared, and then we needed to modify the model slightly in order to incorporate this use case. No, so this only happens when the person interested in this use case raises up his hand, says, "Look, I need to do this," etc. And so the thing with standardization is very complex, because if I want to standardize something, then it is kind of an imposition to the surrounding analysis teams, analysis software, etc. So the which also relates to a discussion that we had in the very beginning of this Discord chat that you can actually go back and take a look, because Henrique was discussing about using DL3 with Hawk. No, so I'm seeing Marco answering standardization is not an imposition, but what I mean is that this data model, it's always coming from the people that need to use it and the people that need to do it. So I can put a very simple example that Matthias will easily understand. So if someone from internally from CTA, as you, Matthias, takes a look at the current format, he will automatically and instantly realize that it will not work for CTA as it is right now. Why? Because for example, the instrument response functions are not complex enough to describe for instance, the evolution of the instrument response functions at certain parameters that are currently not included. No, this is, for example, a very simple question to make. No, but the thing is that as soon as we have some CTA data, or as soon as we have some CTA simulations, including those parameters that are currently not reflected into the format, then we would create an issue, we would create a pull request, then we would incorporate that need into the format, making sure that there will be analysis tools that are able to also include that format. No, so for example, to include Hawk into this format, we definitely need Hawk people that step in and participate into the forum and into the discussion, define also the changes that need to be applied in the analysis tools that will use this format, these files, and then making sure that both the analysis teams and the data production teams will make use of those changes, then it makes sense to change the data format. At least that is how we have worked until now.
Yeah, thanks a lot, Tarek. That indeed explains a lot, let's say, the process here. And certainly I'm not here to at all to criticize this effort, not at all, really, because you already showed in your talk, let's say, the benefits of such standardization. Yeah, it's really visible. You can do this kind of multi-experiment analysis, and that is really the benefits that is also experienced in other communities. And maybe I'm just asking this question a bit more to learn maybe a bit about best practices and experiences of other communities that had also to standardize on such formats before. So on how to organize such discussion and how to create a forum for the experiments and the community to discuss such further standardization.
Yeah, this is why I said that it would be really interesting to receive feedback from people that are actually using FIT standard since a while, but it seems that there is no one at the moment present. Because I guess other instruments had...
Well, that's not true. Sorry.
No, please.
I'm actually responsible for the FITS standard kind of implementation in Alma. And,
okay. So did you start
but we
for
only use it
something
for
that?
images. So
Okay.
this is different. In fact, I mean, let me tell you what it's like in Alma. So we have essentially 3 data formats. We have the archival data format. We have the working data format that is not really stored anywhere, but only used for intermediate products during processing. And we have fits for images. And actually, we have 2 image formats. There's also an intermediate one used only during processing, but what goes into the archive are fits images. So I think this is a situation that is very common in all observatories. I would also regard your new fits format as some kind of export format, right? I mean, people are not working internally with this, or are they?
Yes, it's more of an export format for
that's totally fine.
for us. For Magic is more for the legacy data, let's say.
And the good thing about this is that, you know, if it's a fits file, people can read it. That's for sure. If you follow the fits standard, you don't need to talk about standardization anymore. Anybody who has a fits reader can read it.
Exactly.
Just need to have CFIT.io or you know, some of the F tools or what. and there are also lots of Python tools to read it. So in a way, you are done. People will not get one of your files and sit in front of it as if it was a black box, that it's inaccessible.
No, exactly.
Totally look at it and can explore every corner of it. Question is then, how do you actually extract the image from it, which or the spectrum, which is the thing that you really want. So there you have to provide your not proprietary, but your own special software. And I don't know, that's probably going to be open source, right?
Yes, both the candidates are open source, GammaPy and CET.
Is it some kind of Python module, or how do I?
GammaPy is entirely built on Python. The other tools.
Python 3 module.
Yes. It's an AstroPy affiliated package, so it's Python and it's AstroPy based. The other C tools relies on this GammaLib, which is a C++ library to read different gamma ray astronomical data. This is why it could combine Fermilab and the SCT DL3 together. And then there is a Python wrapper, but you can use it also as a command line tool. It's very similar to the classical F tools.
Great. So yeah, I think you are very close to the final thing somehow. I mean, the question is then only, to make your tools work. I mean, to actually deliver scientifically correct products, you need to think about what metadata does your tool need, and that has to be in your fits file somehow, or in the instrument response function storage. And that is something only you know, that cannot be dictated by the community because they don't know the instruments so well. So there's some kind of part of the standard that simply has to work. And there you need very good versioning, I would say. You need to make your tools aware of the format version that it is reading, so that it does the right thing with the right version of your instrument response function format and so on. So there has to be some part of the code that detects conflicts in terms of versioning, so that the code knows, okay, I'm capable of reading version 1.3 of this fits
data format, yes.
but I'm not able to read version 4, for example, and then it should stop and tell people, update your software. This is a too new file. And then you have all this problem of backwards compatibility. Does a new version of your software, is it capable of processing old old data that have been downloaded 3 years ago, that were using slightly different conventions and all that. But
Yeah,
it's
so
definitely there are solutions for that.
sure.
Yes.
Here, for example, we have Jose Enrique, which he's actually have been working on the provenance aspects of the future CTA analysis. So he might be able to give some insights on it. So I want to very briefly discuss about what you were saying, and also which also connects with the with some of the discussion that we have right now on Discord. So I would say that more than the format itself, like technically the format of how you are storing those bytes of data. So this is more of an effort of defining the data model that we need as a community, in the gamma ray range, let's say, and this was never done before. That's why it's being done now, which is interesting, and precisely because it is not so hardwired with the FITS data format itself. Some of the discussion, for example, here people is discussing HDF5 versus FITS. So this effort still completely makes sense. So it still makes sense to continue identifying how and what needs to be stored, because going from a FITS standardization to any other, to HDF5, etc., would still, in any case, strongly benefit from this initiative. So it is not so much the format, but the data model that has most of the value, at least in my view. And the second point regarding provenance, etc., this will actually be a challenge, because I really foresee in the coming years that many of the current generation Cherenkov telescopes will either stop operating, or operate in a different manner, with CTA as the main observatory in our field. And as Cosimo has presented, it is expected that they create some legacy data products. So we do not expect that those legacy data products will strongly evolve with time. So it seems likely that these legacy products from the current generation will more or less halt in time, at least their format, while CTA will surely evolve. So as you were indeed saying, making sure that the software properly takes that into account, and we really need to make sure that the software handles different versions of the data format, will be crucial, mainly to use all the archive data of the current generation of telescopes.
Yes, if I can go back also to one of Matthias' points that Dirk was also discussing. So Dirk, you said that you store image. So basically the format that you have standardized, I think it's even higher level than the one we are storing, right?
Well, as I said, we have an archival data format that's called the ALMA Science Data Model, that was developed for ALMA and the Very Large Array, and is, so to speak, really special. It's an XML plus binary format. That's our raw data. And believe it or not, it's also essentially a list of events. So there's a big similarity to the Cherenkov telescope data. That is what we use for this part, and that is really large data. I mean, that is can be terabytes.
And connecting to one of Matthias' points.
That is on the archives. And then there are these intermediate data formats that are only used during processing and never really stored anywhere long term. Called the measurement set, never mind. And then at the end, the other archival products are images. And that's where we use FITS, because that's what is really the astronomy standard at the moment. I mean, nobody uses anything else but FITS for images.
And this data format, how was it defined? Is it something internal
ASDM.
to ALMA itself, or
Well,
does
the
it share
ASDM
commonalities with other telescopes? Because, for example, you're using the same software, no?
Well,
As
the
CASA.
ASDM, yes, CASA was originally developed as the designated package for ALMA and the VLA, and it still is, but it has also the ambition to be a general tool for all radio astronomy. And the ASDM came after CASA was already developed, so to speak. The ASDM was developed as part of the ALMA project, hence the A in ASDM. And in order to save resources, VLA also adopted the same data format.
Mm-hmm.
So
and
these
how
two
was it
projects
defined?
essentially came together and put in a reasonable amount of money to pay somebody, or actually a few people, to develop this format.
I see.
Based on a precursor which is called the measurement set. This is something that was developed by the radio astronomical community and published in its second version in 2000. So it's a properly documented format, but it's really only a model. It doesn't really say anything about the implementation, meaning the underlying file format that is used on disk. It's only the design of the database, essentially.
And it was not community driven, as you said. There were
yes, it was community driven.
But as you said, there were these two people hired to, no?
Yeah. Okay, but they took essentially this measurement set, which was a community. Well, I mean, it's not like they did a survey of all radio astronomers and asked them what they think it should be. And
yeah, exactly. That's the point.
I mean, there's only one truth. It's a mathematical problem that has one solution, essentially. And the fathers of the measurement set came up with that solution, and it has proved now over the last 2 decades to be amazingly correct. I mean, nobody has really found any hole in this design yet. There have been not even extensions were really seriously necessary, and the ASDM generalized it further to make it applicable to really all thinkable radio telescopes. And also here, a pretty good job was done. So this is a database that has something like 50 tables, and it really covers all thinkable bases. Only very few tables had to be added in a second iteration, like over the 2 years that followed the inauguration of ALMA. And now it's very rare that any addition is made to that format. So I don't think you can design something like this by committee. You have to really get people who know what they're doing and you know, have the whole idea and the whole concept in their brain and nail it down. That if you get the right people to do this, that the result is normally better than if you know, lots of people just dedicate 10% of their time to think about this now and then. You need to have some people who really work hard and full time on this to really think it to the end. At least that's my opinion. And then, of course, you have a proposal, and you can distribute this to a larger group of people to get feedback, and maybe some people will still discover some small problems in it. But the big design has to be done by a small group. Otherwise, it takes forever, or it will be some kind of Frankenstein thing that is not quite right.
So Dirk, if I may interrupt, so what he describes, the parent of everything is this thing called the measurement equation, which in principle should apply to gamma ray astronomy as well. But I've not seen it applied to anything outside of astronomy. So the mathematical foundation of how radiation is modified by the instrument is the measurement equation, and it should capture gamma rays.
That's true. Yeah, maybe the measurement equation is even applicable to gamma ray astronomy. I mean, we don't have.
Well, it should be, yeah.
Yeah, possible. I mean, a gamma ray observatory is not an interferometer at all. It's the
no.
Yeah, exactly. The point is that we detect like particle hits.
It's just counting events, and the secret is really in the response function. How does your detector respond to gamma radiation coming in from a sources at infinity, so in parallel tracks essentially, and then there's the other thing that's the background. So this background model that you're mentioning, that's also a big difference to an interferometer. So
yes, because in many aspects
could maybe be applied, but that would not be the whole story.
Yes, because in many aspects we are much more similar to a particle physics experiment. So we basically detect particles fundamentally. So
you are a particle physics experiment. It's just that you don't control the accelerator. I mean,
exactly.
Although, if you think about it, it's not that different to a CCD camera, no? I of course, not talking about interferometers, but CCD cameras are like effectively counting photons. So, I mean, come on, it's something similar, no? In the end, it everything comes to a given quantum efficiency, which is our effective area. It comes to a direction. It comes to a given resolution. Of course, we measure simultaneously direction and energy, although we have enormous errors on both, while optical astronomy generally either does one thing or the other, no? Generally, this is starting to change now. But in principle, it's not that different. The problem is that first, our detector changes constantly. No, the performance of our detector changes minute by minute, which in a CCD camera usually does not happen. Usually, the only thing that changes is the transparency of the atmosphere. Very roughly, of course, you can include seeing, etc. But our detector itself changes because the atmosphere is our detector.
Even that is, for example, ALMA has the same thing. I mean, we are permanently observing calibrator sources as references to account for changing conditions. We have a constantly changing detector in an interferometer. It's just the same on a second basis. It's very similar.
Yes, so we should definitely learn from what ALMA is doing.
No, I mean, you have got your solutions. I mean, you've been doing this now for several decades, and I wouldn't. I mean, the big change of paradigm. I mean, I remember when I was working in high energy gamma ray astronomy, I was not using root but PAW, which was the predecessor of root, and we were also using these N tuples. Actually, I introduced that, and this worked very well. And the big difference is that you are much more forced to rely on simulations. You don't have reference sources that you can jump to and quickly check the state of your instrument. There is essentially with a high precision, there is no reference source, not even the crab, because we know now it's also variable, right?
Yes.
And the crab is not up all the time, so you have really no reference that you can fall back on, and therefore you need to use simulations to a much larger extent than other fields of astronomy. but I guess if you have big set of simulations parameterized by different atmospherical conditions, it should be possible to cope with that. I mean, as far as I can see, you've got the solution already. I don't think you have to adapt too much to other fields of astronomy. You have very specific conditions, and you can, how shall I say, be self-confident enough to use your own methods.
Yeah, so
as long as you package it properly, it will be fine.
So the key here is going from experiment to an observatory, no? So that's the main step for us, and certainly a lot of work needs to be invested into this, because it is clearly not ready yet for several, for example, observing modes that CTA could have, or several other things. But the key aspect here is that the decisions, let's say the most important decisions, I think that are already taken. Let's say it will be FITS or HGA5 or equivalent, but containing event-wise data plus instrument response functions, and that is the level that we will be, let's say, opening to the community, sharing, and that will be the input for science tools. So as all this has been already, so everybody converged on this, etc. So then all the probably more complex technical details, which include what you were discussing about all the Monte Carlos required for a decent calibration. As you were saying, our instruments literally cannot be directly calibrated. so we need to rely on a whole complex system of calibrators, which I could bore you for hours. But yeah, at least regarding to this, let's say, data standardization or data model standardization, it seems that at least many of the problems of the technique will rely underneath internally into CTA, and the user, the future guest observer and science tools user will essentially not feel the difference with for example, other fields of astronomy. So they will not feel, at least will not dramatically feel, the difference between using, for example, Fermilab data or CTA data. That's our main objective, no? And by incorporating both the event lists and the instrument response functions, as by defining, for example, the good time intervals that Bruno was referring to, etc. By doing all these tiny things, we expect the process to be quite uniform. So it will be a relatively simple, well, not simple, but a relatively similar analysis as the one that is currently being employed in the high energy astronomy field. So I guess that is good news. And Cosimo, we are getting near to the time of the.
Yes, I think we have 3 minutes, right?
Yes, indeed. Yeah. So that's why I was putting the camera on, just to remind you that. Sorry, that's my duty.
No, don't worry. I think Marco wanted to talk. He had the hand raised for a while, so maybe we can take some comment from Marco.
Yeah, sorry, I didn't want to interrupt you because you were having a really good discussion, so no need there. I just wanted to clarify my view that is, of course, biased by the work that I'm doing. And I think that the format that you are developing and dealing with, it's really a good one. And the way that you are tackling the solutions for formats, how this is used, what software do you attach to it, what communities you can involve, what projects or experiments you are able to attach to. This is already great. I think it's really at a good major level. So if you are, I think that what you are dealing with now is tackling the interoperability with other let's say, domains of observation in a sense. So multi-wavelength, multi-messaging, it's always in that it's in the same direction. So if you want interoperability there, you have to explain to the other communities what are your needs. So the IVOA approach there, of course, comes from the sky, from the night sky observation. So it has simple basic requirements at the start. It had simple basic requirements at the start that were positional in the sky, bandwidth, descriptions, and things like that. So 4 major axes, if you want. So to positional, spectral, time one, polarization, you have possibly similar needs, but written in different ways. And the fact that you are pointing to, that you explicitly said more than once that you have events, event lists that are what I think in the IVOA are modeled or can be modeled in the sparse cubes. Well, that's some use cases and requirements that I think the IVOA will be really happy to listen about, and maybe we can join efforts at that point, because the format is fine for archiving, for analysis, for whatever. Then you have to make it well. Now again, buzzwords. You have to make it discoverable. You have to make it interoperable, and at that point you'll have more software instruments and tools that can deal with gamma ray and other data together. Just a clarification. My intent was not to criticize anything.
No, thank you.
In fact, I mean, I don't know if maybe, I mean, if this channel can be left open if you want to continue to discuss, or if you want to continue the discussions on Discord. I mean,
yeah, I think we can continue on Discord. Also because me and Tarek are supposed to be in the Magic meeting in the meanwhile.
Okay, yeah. Yeah, I also have a similar problem. I have to be in another meeting. Okay, so do you want to give a final word, Cosimo or Tarek?
Well, thank you very much. I think there was a good participation and nothing. Thank you.
No, I'm actually positively surprised about all the discussion we had. Like we were worried, like there would be like cricket sounds everywhere. No, it was
luckily there was Dirk that he passed the entire electromagnetic spectrum, so he could comment on.
Okay. Very good. And I have a little message from the program organizing committee on the log. So to ask everybody to check the poster channel in Discord, because there is some info there about how to sign up for the lightning talks today, for the dedicated poster lightning talk session, which is later on today. So this just so please go and have a look at the poster channel on Discord, and you'll find all the information there.
Mm-hmm. Okay.
Okay. Very good. Many thanks, Cosimo and Tarek, and all the people for participation.
All right, folks. Amazing discussion, really good. And we'll reconvene at 11 a.m. UTC.